la PowerGap e risultati. E ora tra poco ci sarà. Infatti adesso si vede che si trova. Veramente bene. Quindi noi mi fanno lavorare tranquillamente sullo sfondo senza problemi. Ma se non ci sei adesso si vede nella tua... Vai, vai. Non dovresti... Ok.
Francesco, ci sei?
Hello, can you hear me?
Hi, Bucci-san. How are you?
Hi, just fine. How about you?
Fine, fine.
Okay, good.
At least we hope so.
Okay.
Hi, Nils.
Guarda, mi senti?
Hi, good afternoon, everybody. Good afternoon, good morning, good night.
If you
And
want.
we can start now the pre-session. And Mark already checked Veronica. So, Nils, you are there. Can you try to...
Can you, first of all, can you hear me?
Yes, perfectly.
Can I try to share my screen? I never tried this before.
Yes. Just wait a minute. I will... I'm giving you... Now you should be able to share the screen. There is a button on... Did you find the share screen? Is on the side of stop video and stop audio in the bottom of the page.
What happens? Okay.
Did you find it?
Yes. But when I push it, nothing happens. Maybe I should go and get I have a colleague here who is much more computerized than I am.
Oh, okay.
So maybe
in any case, we have your backup presentation.
yes.
So,
okay. He's just sitting there, so I'll be back in a minute.
Okay, perfect. Okay, we can go ahead in the meantime. Hi, Matteo. You are the presenter of the third work. Can you try to speak? You are at the microphone mute, perfect. And just a minute, yes.
Okay.
Just only a minute. I will set you as speaker, so you can. You should see your share screen
share
button.
Screen, yes.
Okay.
Screen.
No, I'm running for the
Okay. It works.
You can see the screen?
Yes, perfect.
It's working? Okay.
Okay. Thank you.
Lov til at dele din skærm. Men det synes jeg, han havde gjort.
Okay, so I can stop sharing.
Okay, perfect.
Den er grayed out nu, så nu kan du ikke. Nej, okay.
Niels, just a minute. I have to give you again the. So, Matteo will stop your screen sharing, and we can try again with Niels. Okay.
Okay, then you should give me the right to do it.
Yes, now you should have the right to share the screen.
I can't see that this happens.
It's not enabled?
No, it's grayed out. It's.
Oh, that's a problem, because I have. Yeah. For me, you are enabled to share the screen.
Okay. Kan jeg få det der? Hvad står der der? Systemindstillinger. Yeah, let's try that one, yes. Jeg trykker. Nå, nu kommer.
Hi everyone.
Ciao, Francesco.
Ciao.
Ciao.
Nå, hvad fanden.
C'è l'audio, non so.
C'è l'audio, sì. C'è l'audio.
Hello. Hello everybody.
Hi, Ada.
Hi Ada.
Hi. Because I switched from Skype. Okay. I'm waiting for your instruction to sharing.
Okay. Just a minute. We are verifying all the presenters.
Okay.
Oh, we have Ebuchi-san.
Ja, den ser ikke
Hi.
nok ud.
Can you try to...
Det er det der, vi
Yes, please.
Anonym. Prøv lige at klikke på det, hvad er der?
Okay.
Nej.
Ebuchi-san, can you try to speak? Just to verify.
Hello.
Hvad er de andre bare for?
Can you see my screen?
Nej, men de
Is
andre...
something is going on? Okay.
Klik på
And
der er et eller andet der.
this is the full screen.
Okay.
And can you hear me?
Yeah.
Det er fejl.
And this is raise a pointer.
Okay, perfect.
And
Very good.
okay.
Thank you.
Yes, thank you. So everything fine. Okay.
Yes.
Sharing.
Okay, you can stop sharing.
Okay.
Thank you.
Okay, thank you.
Okay, Ada, would you like to try? Audio seems working.
Skal jeg lade være med det?
And just a minute, I will give you.
Fordi ellers kan den jo ikke...
Okay, now you are enabled to share the screen. You should see on the bottom of the page the button share screen or condividi. Does it work?
Jamen, det må være sådan noget, og bed om adgangskode efter boglus eller skærmskåner. Det er jo ikke, det har ikke noget med det der at gøre. Der burde ikke være noget.
Funziona?
Prøv lige at gå...
Ada.
Og stoppe det.
Do you
Prøv lige at klikke på
see
den
the button to share screen?
No, because I don't know. Now see, yes, I see share. Okay, I try.
Yes, please.
kamera, nej, der er
Okay.
ikke kamera. Det er kun kamera. Nu vil jeg se, om der er et eller andet i den der. Ikke den. Den til højre for.
Do you see something?
Det er bare.
Yeah, something is going on.
Yeah.
Not yet, but something is
See,
happening.
just charge.
Nej.
Because listen, yesterday I got some network problem. I don't know why. This is the first time.
Yeah.
If ever, what happened? I get out and then get in again. Do you have a
Yeah.
procedure to manage abrupt interruption of the
Okay.
network?
And actually, now that there is a warning on your picture that is low bandwidth, low bandwidth connection. So possibly your bandwidth is not enough for sharing video. So now we have the presentation.
That's very,
Ja.
very strange because I work every day with this, sharing whatever.
Possibly
How does it going now?
the issues is another one. Yeah. Just in case, you can try to switch off your cam and leave only the presentation, just to save a bandwidth, just in case. But now it seems working. Can you go ahead with the presentation, just to verify if the slide?
Prøv lige at se, om jeg kan gå noget op.
This is it's not the actual one, but anyhow. Do you see something? It's too
Yes.
fast.
No, that is always the same frame.
Okay.
Doesn't change.
Listen, I get out, get in again in the
Okay.
in the room. Okay.
Okay.
In few minutes. Bye. Ciao.
Okay. Ciao.
Okay, you hear me again?
Yes.
We have tried to find out, but we cannot activate the share button.
I can try to give you again the role of speaker, and you should see the gray share screen button become active.
It doesn't happen.
Just to wait a minute.
Okay.
Ja.
Now I see that you have the right to enable the screen sharing.
I cannot see that, so I do it. It doesn't help me. So maybe we should just, if you accept that you show my presentation and I just comment.
Yes. You simply say next for changing the slides.
Okay.
So the presentation is the same you uploaded. No modification, no last minute changes or nothing.
No.
Okay.
No. So it's
Okay. Good. So we will try to resume it and show for you. Okay.
Yeah, okay, we'll do that.
This is unfortunate. Okay, we have a trouble with the last presenter. Eric, are you there? I see you, but I can't hear. Okay. I can't hear you.
Right now, or
Yeah, but it's a very, very low volume.
Preferences.
a bit more volume.
Yeah, try to increase or to speak closer to the microphone.
Yeah,
And we are not able to open your presentation.
Oh, really?
Yeah, the Acrobat says that an error occurred. But now let's try to, if you can manage it by yourself, is better. Okay.
Meeting. So
Try just a minute. I am going to give you.
Du kunne ikke finde ud af, hvad der var galt på forhånd. Altså, hvis det er Zoom.
Ja, så kunne vi selv have testet det.
Okay.
Okay, can you see my screen now?
Now, yes.
Okay, then.
Try to.
Put in full screen.
Okay.
Does that work?
Okay, seems working.
Okay, perfect.
The only issue is if you are able to increase a bit your volume, because we are very low.
Okay.
But it seems working. Ada, would you like to try again? You are muted.
Sorry.
Okay.
I'm waiting for.
Yes, I'm giving you the
Okay.
Now it's working. But
to switch through the slides.
okay.
To see.
Okay. We see some Potenzio browser, Mac App Store.
Sorry.
Presentation.
Sorry. I don't know how to choose. I come back. How to choose?
You should see the possibility to share all of the entire screen or a particular window or app.
App. I'm looking for this. Disattiva, condividi.
You should have something, a sliding window on the top of your screen.
And I have to this. You see?
Is just something is going on? You have to wait a bit. No, it's the same of the previous try.
Oh,
now it has arrived. Try.
Because I'm sharing my screen.
Yes.
I connect your screen.
Now it seems working.
I see the first page of my presentation.
Yes. Now yes. Try to get full screen and then move forward and back. Yes, try to move forward and back. Okay. The third.
Jeg fandt lige noget, der var interessant.
Okay. I believe it will work now. So good.
Okay.
We can stop.
Okay, then I don't know. Let's say I switch off everything. I keep open only the presentation, so I'm sure just not to have problems at the beginning, just to not to waste time. Okay.
Perfect.
And how do you say alert us of having 2 minutes time? You make it bling.
We believe that the bling is the ringing or something like this is quite annoying at the end. So the chairman of the session will interrupt you for a while and will say that 2 minutes left or something like this.
Okay.
But the chairman for your session would be Simone Pettinato.
Okay.
Hello.
I just it works. I can.
Yes, I can. You can release the screen, and I will give the floor to.
Det virker barok. Det virker som det modsatte, ikke?
Jan, would you like to try your presentation?
Yeah, sure.
Okay, audio seems working okay. Just a minute, I give you the role of presenter. Now you should be able to share your screen.
Just a second.
Yes. Something is happening, indeed. Okay, we see your first slide.
And what about the presenters mode? Work?
Yes, try. Okay, seems try to go forward and back. The second, third. Okay. It seems working.
Okay.
Good. Thank you. You can stop share now.
Okay.
And who is left? Ignacio Corbeia. Is Ignacio Corbella there? No?
Ja, okay. Eller hold op, det driller dem. Så jeg...
Can I talk now? Or are you doing something else?
Niels?
Can I try
please.
once again? Can you try to let me share my screen? I did a small change, so maybe it has happened. I don't know.
Okay.
Yes.
Okay, now it looks different.
Oh, good. That's good news.
Yeah. Something is happening.
Right, og så skal du bare vælge PowerPoint.
Den ligger om på skærmen, ja.
Kan du ikke vælge den dernede?
Nej, men det er det er ikke en PowerPoint, det er en PDF. Det var da ja.
Jamen kan du ikke skal du ikke minimere den der? Ja, det kan du måske.
Hvorfor kan jeg ikke bare... Den der kan jeg faktisk ikke.
Ja.
Det var den her, jeg ville tage.
Ja.
Seems working now. We can see your desktop.
Well, you know.
Okay.
Keep it just 10 seconds.
And
okay, now the presentation.
And now it's in can you see it?
Yes. It's in full screen mode. Try to go back. Yes. It seems working.
Okay.
We are in slide 11 now.
That's fine. Yes. That's fine.
And we're just only seeing your presentation, nothing else but your presentation.
Okay, yes. Good. So to do that, Jen.
Okay, it seems working. Good.
So you take me off again.
Okay.
Yeah. Okay.
You can do it by yourself.
Den ser du. Den ser du.
Nå, det er kun mig, der ser det.
Ja.
Can you hear me?
Nej. Hvorfor får jeg ikke...
Niels?
Du skal stoppe skærmen.
Nå, skal jeg stoppe skærmen? Det kan jeg da ikke. Hvor er den?
Få den der op igen. Den du lige hentede. Den der Louise.
Den her?
Cisco, yes. Nej, den der. Hvad er den henne?
Den er væk. Den røg derop bare.
Avevi sentite?
Sì, Simone, io ti sento molto male però.
Ok, aspetta.
Molto male.
Così?
Ora un po' meglio, sì, è un po' rimbombante, ma insomma meglio.
Mi
senti così?
Det var lige at minimere den
sì.
der.
Meglio?
Ok, vai, andiamo avanti.
Plejer at være en standalone et eller andet.
Eric, are you there?
Yes, I wanted to ask if it was better right now for the
Yes,
sound.
we are ready for you. Okay, just wait a minute. I will give you the ball.
Yeah.
We tried the sharing already, but we can retry it. But is the sound quality better?
Okay. I'm giving we have two Eric in the session. Apologize. Is Eric Canterier?
Yes.
Okay, you should have the right to share your screen now.
Yes, I will do it.
Okay, please try. Microphone seems working. We can hear you very well.
Yes, for the microphone it's okay.
Yes.
I just try to share the screen.
Okay.
Is it okay?
Okay, we can see. Try to the full screen mode.
Yes. Do you see the slides?
Yes. 4, 5, 2. Okay.
It's okay?
It's
Thank
okay.
you.
It seems working perfectly. Thank you.
Thank you very much.
You're welcome. Okay, so we are all checked. No, there is still one presentation. Ignacio Corbella is not there.
I don't see him.
Can I talk to Simone?
Yes, can you hear me?
Pardon?
Can you hear me?
Yeah, I can hear you. Can you?
Okay.
And,
You are co-chair with me?
Yes.
Yeah.
So should I take 4 and you take 4?
Yes, I can manage the first part, so you can present.
Okay, so you manage the first 4, and then I.
Yeah.
Okay,
Yeah.
good. That's all.
Thanks. Bye.
Yeah.
Just a small question. Can I confirm that the sound quality is now right for everyone?
Yeah.
Yeah. Yes.
Okay.
Apart
Perfect.
from the. Yeah. It's working better than the first try.
Okay, perfect. Thanks a lot.
So we will start with the keynote in a few minutes. We are still waiting for the last presenter, Ignacio Corbeia, and I hope he will join before the starting the conference. I still don't see the presenter of the fourth work, Ignacio Corbeia. Is not there. So the last call. As the presenter of the fourth presentation, Ignacio Corbeia joined? No.
No.
It seems there is not.
Okay. Shall we start now? At 2 o'clock. So let me give a very quick introduction. Dear participants, welcome to the third day of MicroRad 2020. Today we have the first of the 3 planned keynotes for international space agencies. In particular, we'll speak Naoto Ebuchi from the Japanese Space Agency. At 2:30 p.m. Central Europe time, after the keynote, MicroRad will split into 2 parallel sessions. The first in Room 1, Advanced Techniques for System and Sensors, and the Cryosphere in Room 2. At 6:30 p.m., we will have the side event RFI discussion on a dedicated room. For people interested in joining this event, the link on WebEx will be published on the MicroRad 2020 website before the beginning of the event. Let me provide you my usual annoying recommendation. Each presenter has a reserved schedule of 10 minutes for presentation plus 5 minutes for question and answer. And I would warmly recommend the chairs and the presenters to keep the schedule. Please note that all the participants connected by WebEx can mute and unmute their microphone to ask questions to the presenters. We will also try to report the question from the YouTube channel, but this is not, from our experience of the previous days, is not really straightforward, so we will try to do our best in this. And I would also ask the session chair to have a look. The participant presenter to the second session are invited to connect to the session during the break. And that's all from my side. I'm now honored to give the floor to Naoto Ebuchi, that will speak on behalf of the Japan Aerospace Agency about the present status of MSR2 on GCOM W and the introduction to MSR3 on GOSAT GW. Dear Ebuchi-san, the floor is yours.
Hey, thank you.
Just a minute.
This? Yes.
I have to enable you to share. Okay, you should be now able to share. Good.
Okay. Thank you for your kind introduction, and good morning, good afternoon, good evening, everybody. I'm Naoto Ebuchi from Hokkaido University, Japan, and I'm also working for the JAXA as a project scientist of AMSA-2 mission. Title of my talk today is the present status of AMSA-2 on GCOP-W and introduction to AMSA-3 on GOSAT-GW. The most of the presentation materials in this talk are contributed by these courses in JAXA. This slide shows the timeline of JAXA's Earth observation missions. We have AEROS series, which carry the L-band synthetic aperture radars and high-resolution visible sensors. The main target of the AEROS mission is disaster monitoring and exploitation.
We don't hear anything.
Hi, hello.
Yes, now it's working.
Okay.
Now it's working.
Okay, sorry. This slide show the JAXA's Earth observation missions, and we have AEROS series, and also the MicroRad radiometers greatly contribute to the investigate the water cycle. At present, JAXA operates the two missions, GPM for precipitation observation, and AMSA-2 for wind, SST, water vapor, and rainfall. AMSA-2 will be followed by the AMSA-3 on GOSAT-GW, Global Observing Satellite for Greenhouse Gases and Water Cycle. The third column is visible and infrared radiometers for vegetation, cloud, aerosols, and SST and ocean color. And JAXA also contributes to the ESA's Earth-Scale mission. The fourth columns show the emissions for greenhouse gases monitoring. Now we have a GOSAT-1 and GOSAT-2, and GOSAT-3, or the follow mission, will be combined with the AMSA-3 and into the GOSAT-GW mission. So this is a history of Japanese microwave radiometer missions. The history was started in MSR on MOS-1 satellite in 1987, and AMSR and AMSA-E was launched in 2002, and AMSA-2 was launched in 2012, and there continues observations until now. And you can see the improvement of the sensors. So we get more channels and bigger antennas and higher resolutions. Our following mission, AMSA-3, is now under development and scheduled to be launched in the Japanese fiscal year of 2023. So this is a summary of AMSA-2 on GCOP-W. AMSA-2 has 7 frequency channels with the dual polarization from 6.9 GHz to 89 GHz in dual polarization. And our 2-meter antenna scans 40 rounds per minute and creates the 1600 wide swath. This is a list of the AMSA-2 standard data products. The data products cover the atmosphere, ocean, land, and cryosphere. And these data are freely available from the Japanese JAXA's portal site for scientific and academic users. After a very short registration, you can download these data. This panel shows the example of the snapshots obtained by AMSA-2 on a particular day of the 1st of July 2013. This is sea surface temperature, sea surface wind speed, vertically integrated water vapor, and precipitation. JAXA provides a website named AMSA Viewer to quickly visualize the AMSA's data and to create such pictures. By using these snapshots, we can produce the level 3 gridded datasets. And these are examples of monthly means in December 2012. These maps of snapshots and gridded data can be easily produced at the JAXA's portal site and AMSA Viewer site if you have interests. JAXA also provides the research products from AMSA2. The algorithm to produce these products were proposed and developed by the principal investigators. And you can also download these research products from the JAXA's website, but the URL is different from the main portal site. And this table shows the essential climate variables designated by the GCOS Global Climate Observing System. AMSA series can contribute the 7 of these parameters. Okay, good. Now I will briefly introduce some scientific applications of AMSA2 data. The JAXA produces the global precipitation map named GSMAP. This is an example of animation. The spatial resolution is point by point degrees or 10 kilometers, and temporal interval is 1 hour. So this map clearly captures the global distribution of the rainfall. And this GS map is now widely used for the water resource management, dam operations, flood and drought predictions, and agriculture, especially in the Asian countries. You can access the precipitation GS map precipitation maps and data following this link. A long-term global sea surface temperature record over the 18 years obtained by the AMSA series and used for the detection of global SST trend and ENSO event monitoring. This diagram is composed by the Japan Meteorological Agency using various sources of the observation data, starting in 1890s, and it clearly shows the warming trend of 5 degrees in 0.5 degrees in 100 years. The AMSA series covers only the last section of 18 years, but observation by AMSA-E, WINSAT, and AMSA2 also clearly show the consistent warming trends, and we can also see the some hiatus in the warming trend. Using the SST data, we can also monitor the ENSO events, El Nino and Southern Oscillation events. This is a time series of the SSA anomaly in the NEOS 3 region. You can clearly recognize the warm and cold events, El Nino and La Nina, in these 80 years. And by combining the SST data with scatterometer vector wind and altimeter sea surface height, we can see the onset of El Nino. The horizontal axis is the longitude along the equator, and vertical axis is the time from the January 2014 upward. And this is the zonal wind speed from the ASCAT scatterometer, and this is the sea surface height anomaly from the altimeters, and this is the SST anomaly from the AMSA2. So westerly burst in the western tropical Pacific triggers the Kelvin waves, and the Kelvin waves propagate eastward across the tropical Pacific, and then finally generate the warm SST anomaly in the eastern Pacific. This July, we have a very heavy rain in Japan, and AMSA2 observed the high SST anomaly in the south of Japan, and it clearly corresponds to the higher water vapor anomaly in the around the bayou front. And we can conjecture the humidity supplied from the warmer SST ocean result in the heavy rain over Japan. But the detailed studies are now underway. And the AMSA series has also contributed greatly to the sea ice extent monitoring over polar oceans. These two panels show the snapshots of the sea ice concentration observed by the AMSA-2 in the Arctic and Antarctic seas. And this is a time series of sea ice extent in the Arctic seas. The time series started with the SMMR and SSMI, and AMSA-E, AMSA WINSAT, and AMSA-2 contributed to extend it. And as you know, the minimum record was observed in 2012. This is the minimum record in the history. And the second minimum used to be observed in the 2007. But this year, the second minimum was observed in September 2020. This is the interannual variation of the sea ice extent in September. And this is the 2012, and this is 2020 and 2007. Comparing these data, we can obtain the consistent sea ice record in the Arctic, Antarctic, and global oceans. So let me talk about the follow mission AMSA-3. So AMSA-2 is now 8 years old, and that exceeds the designed mission life of 5 years. However, as far as I know, the satellite and sensor are very healthy, and every parameter is within the normal range. I hope the AMSA-2 will survive for a few more years at least. And now JAXA plans a follow mission AMSA-3. It will be carried by the GOSAT GW satellite and expected to be launched in the Japanese fiscal year of 2023. The top priority of AMSA-3 mission is continuity of AMSA series. So we try to produce the long-time continuous data records over 30 years for climate studies. And we also enhance the operational use of the near real-time data for weather forecast, including typhoon monitoring and fishery in the near shore and offshore regions, and also the navigations on the Arctic ship routes. In addition, we challenge to obtain the new geophysical parameters with new frequency channels. So this is the configuration of the GOSAT GW satellite. We have the AMSA-3 and also TANSO-3, an optical sensor to detect the greenhouse gases. The orbit is very similar to GCOM-W, but the altitude is slightly lower. And this list shows the specification of AMSA-3. All the frequency channels of AMSA-2 are maintained, and red indicates the new channels. So we add 3 high-frequency channels in G-band for snowfall observation and humidity sounding, and a 10 GHz channel with broader bandwidth for high accuracy SST measurement. So these two panels show the improvements by the higher frequency channels. So AMSA-2 cannot observe the solid precipitation, snow, but the AMSA-3 can detect the solid precipitation by using these higher frequency channels. So we can extend the precipitation maps to higher latitude in winter. The addition of the 10 GHz channel with broader bandwidth will contribute to the high accuracy SST measurements. This is the SST from the AMSA2 10 GHz channels, the 7 GHz channel. So the spatial resolution is 50 kilometers. And this is 10 GHz channel, SST. And spatial resolution is now down to 30 kilometers. But this SST field looks very noisy. So we expect the new 10 GHz channels with improved NEDT may reduce the noise and provides higher resolution and higher accuracy SST. And this is a list of AMSA3 data products. Red indicates the new products. So several new parameters are added to their standard products and research products. And this is the last slide, and this shows the current status of AMSA3 development. We completed MDR and SRR in 2018 and SDR in 2019. And now the PDR is now underway and will be completed within this year or early next year. So starting from the AMSA-E in 2002 and followed by AMSA2 in 2012, AMSA3 will achieve the global data records over 30 years. So we believe the observed data will significantly contribute to the scientific researches and practical applications related to the global climate and water cycle. Thank you for your attention, and I welcome your questions and comments. Thank you.
Okay, Ebuki-san, thank you very much for your presentation. There are some questions, comments. Okay, I have a question. Can you give some more detail on AMSA3 spatial resolution? I mean, especially you talk about radiometric resolution.
Okay.
Yes, thanks.
Okay. Probably. Okay. This is a list of the frequency channels of the AMSA3, and this is the spatial resolution. It depends on the frequency, and for 7 GHz, the spatial resolution is 34 by 50. Is it right? Yes, the 34 by 58 kilometers. And the 10 GHz, it has about 20 by 40. And wow, the higher frequencies, the spatial resolution is 5-6 kilometers. Is this what you want?
Sorry?
Is it okay?
Oh, yes, yes. I read that there is another comment question from Kathleen Present that asks, any additional information about the water vapor retrieval over land?
Yes, this is the probably water vapor over land. Okay, so what lands and temperature? So yes, water vapor, liquid cool. So no, not here. Okay, probably research products. I guess soil moisture vegetation, land temperature vegetation, water content. Wow. Total crystal water over land. Is it right?
Yeah.
So this is the new products that proposed by the one of the PI, and I don't know the details of the algorithm, but probably I can give you the reference or something like information about the new algorithm. But the precipitation overrun is only given in the land, but except ice and vegetation. So it's very limited, but we can get some information.
Okay. There is another question from George also. Is the new wider bandwidth X-band channel expected to experience an increased impact on of RFI?
Yeah, I'm not sure, but so wider bandwidth may have more risks to the influence of the RFI. But at present, this broader bandwidth or higher resolution necessity request comes from the fishery around Japan. And we start with the RFI conditions around the Japan islands by flight and underground measurements, but then, we can get some information. But we cannot guarantee that this kind of the RFI free condition may we can extend the everything into the world ocean. But let us try.
Okay. There are other two questions. What will be the sampling interval for the 37 gigahertz frequency on MSR3?
33 gigahertz.
37.
37.
Yeah.
36.5 gigahertz.
Yeah.
Yeah. And sampling
interval.
Intervals. Wow. I don't know the exact number, but the sampling interval is 5 to okay.
Yeah.
5 to 10 kilometers. Yeah.
Okay. Another question is KA band spatial resolution is 7 by 11 kilometers. What about its sampling interval? Okay.
This question has actually already been answered by Misako Kaki on the chat.
Okay.
So the sampling interval is the same for all channels. Is right.
Like.
Okay.
Okay.
Thank you.
So, any other questions? Comments?
I have a comment. So as you possibly know, we did a lot of work before from using MSRE, and then now with MSR2, so we are very happy. We will have also MSR3, and it seems that the JAXA intend to give some continuity to this mission. So
Yes.
that there are possibly far future now, but there are also plans for giving something like EUMETSAT is doing with the METOP second and the next generation to have a long and far horizon covered by this very useful kind of instruments.
Yes. Okay, it's a very difficult question to answer. So we are discussing the continuity of the MSR 4, 5, 6, 7, but I'm not sure. And also, the JAXA is a research and development agency and not operational agency, but a meteorological agency. So we think about the continuity for the climate studies, and also we need some improvements of the higher resolution, more channels, or more products, and something like that. So for a mission after the MSR3, I don't know, but we have to start the discussion as soon as possible.
Okay, good. So hopefully it's good news for researchers involved in using the data and products from this satellite. Thank you very much.
Okay, thank you.
Okay. Any other question? Comments?
Nothing nothing more from the YouTube chat.
Okay.
So
thank you very much. Okay.
You're welcome, and thank you for your very interesting contribution. I think this closes the keynote, the first keynote of the MicroRad 2020. and we will start in a couple of minutes. We are almost perfectly in the schedule with the session in room 1 is the advanced session in room 1 and the cryosphere session in room 2. Okay. Thank you, and stay connected for the prosecution of these interventions. Okay, I think it's time to start the second part of MicroRad 2020. From this moment, the MicroRad will split in 2 parallel sessions. In this room, we will have advanced techniques for system and sensors from now to 4:30 p.m. And in the other session, in the same hours, we will have the cryosphere session. So participants interested in cryosphere, please use the other link for the second room on WebEx. And now I'm giving the floor to Simone Pettinato and Niels Skov for the first part of the Advanced Techniques for System and Sensor session.
Okay, thank you. Thank you, Emanuele.
I'm going to release my screen.
Yes, I was searching for Gonzalez. I don't see him.
Yes.
In the chat.
Yes, she's Veronica.
Yeah, I'm here.
Okay. Okay.
Just a minute. I'm going to give you the ball. So now you should be able to share your screen. Yes, it works.
Okay, can you see my screen?
Yes, it's working.
Okay.
Okay, so Veronica is going to present a triplet collection analysis for 2 error-correlated datasets, quality assessment of osmosis data. Please, Veronica, you can go.
Okay, thank you. Good afternoon to everybody. I'm presenting a new methodology of the triple collocation analysis for the specific case of having 3 datasets, 2 of them with correlated errors, and in particular we have applied this formulation for the quality assessment of osmosis data. This methodology is in the context of the error characterization of satellite observations, which is crucial for blending observations for multiple datasets into a unique dataset, and also for assimilating these satellite observations in numerical prediction models. The triple collocation has been widely used to assess the errors and the quality of many geophysical variables, remotely sensed with different instruments and at different spatial scales. And we focus in the error characterization of remote sensing variables, where having 3 collocated and completely independent datasets is unlikely. We have developed a new formulation that is called the correlated triple collocation for the case, as I said, of 3 datasets that resolve similar spatial scales and with 2 of them having correlated errors. In fact, we derive error maps from this analysis that allow us to characterize the quality of the different datasets at each point in the map. The idea is that we have 3 series of spatially and temporally collocated measurements. X can be expressed in this way, and we want to estimate the standard deviation of errors of each one of the measurements. We are assuming that the errors of measurements 1 and 2 are correlated with a given covariance, but they are uncorrelated from error measurement 3. We are assuming that the 3 datasets resolve similar spatial scales, so we neglect the representativeness error. And we are assuming that measurements are assumed to have intercalibration factors equal to 1. The idea of this methodology has been designed to ensure a maximum number of positive estimations of the error variances in order to converge faster to the real values and be less sensitive to statistical fluctuations. This allows us a reliable estimation of errors with a limited sampling size. I'm not going into details of all the formulation, but only give the idea and the final formulas. You can find the complete formulation in this paper, in the reference on the bottom of the slide. We have looked for a linear transformation of these measurements 1 and 2 that present correlated errors into 2 measurements with errors uncorrelated. For that, we define an auxiliary scaling parameters U and B. In that way, we can compute the second order moments of the uncorrelated error measurements. And finally, we can express the error variances and the error covariance of the original measurements, the ones that present correlated errors. In fact, we are using this formulation that is highlighted here in order to obtain the error variances for the 3 datasets and also the error covariance between measurements 1 and 2. We have applied this methodology to the error characterization of ELBA and brightness temperature datasets. This study is in the context of analyzing improvements and limitations when introducing in SMOS L1 data some new algorithm. In fact, we have 3 brightness temperature datasets. The reconstructed brightness temperatures from the SMOS operational product, the reconstructed brightness temperatures from SMOS operational product when we apply a method that is called nodal sampling, that in fact reduce the RFI contamination and other artifacts in the images, and the brightness temperatures provided by the SMAP radiometer. We analyze global brightness temperature maps at surface that we generate every day. We have a long series of 18 months. And in fact, as you know, SMOS has a multi-angular incidence angle capability, but we characterize this error for a reduced range of incidence angles in SMOS from 37.5 to 42.5 around the incidence angle of SMAP, that is 40 degrees. We expect higher errors in SMOS TV because the radiometric sensitivity is worse at that incidence angle and because of the RFI contamination. Remember that SMOS has not RFI mitigation on board. The objective, in fact, of this analysis was to assess the performance of nodal sampling version 2, particularly over RFI contaminated regions, but it was analyzed globally. Here we are showing the results that we have over land. In fact, we are showing the error standard deviation for each one of the 3 datasets. On the bottom maps, we have SMOS, and in In the bottom, we have SMAP and the RFI probability map for the same period analyzed. And if we look at the SMOS errors, we can see that when we apply nodal sampling and we compare the top maps, we can see that errors concentrate around the RFI sources locations, as you can see if we compare with the RFI probability map. So we are reducing the contamination by RFI to the locations of the RFI sources. If we look at the differences in the map on top, we can see the differences between the error of the operational TV and the error when we apply nodal sampling. You can see that general we have reddish colors, so the error is lower when we apply nodal sampling. On the bottom, we have the histograms for the global analysis. We are reducing on average 1 Kelvin when we apply nodal sampling, and when we consider the region more affected by RFIs, that is Europe and Asia, the reduction is about 1.45 kelvins. In fact, the improvement is obtained in the 80% of the points in the map. For the rest of the points, that is, errors are higher for nodal sampling, are located very close to coasts, and in these blue spots, that corresponds to the locations of the RFI sources. That both are known issues of the nodal sampling version 2 and are being improved in the next version of the nodal sampling algorithm. We have analyzed also these results over the ocean. You can see here the errors from SMOS operation and when we apply nodal sampling on the top maps. You can see that there is a significant improvement over strongly RFI contaminated seas. You can see, for example, Japan, close to Madagascar, the Mediterranean Sea, in the Gulf of Bengal. You can see in the bottom right map the difference between the two SMOS errors, and you can see that in general we are improving significantly the error that we have when we apply nodal sampling. In fact, we are reducing errors in the 80% of the points of the map. If we zoom in some particular regions, for example, over the semi-enclosed seas, you can see that we are improving. The error is lower when we apply nodal sampling too, except in pixels very close to coast that we have higher errors when we apply nodal sampling. It's the same in the bottom map over the Arctic, that you can see that we have larger errors close to ice edges. This is due to the known issues of nodal sampling version 2 close to coast and ice edges. As I said, with the new version of nodal sampling, version 3, we are improving a lot these artifacts. And we have analyzed which is the average error reduction led by nodal sampling with respect to version to the operational version. And you can see here the error reduction in kelvins
Veronica, you have 2 minutes left.
Okay, thank you. The error reduction for some of the more RFI contaminated regions. We have also applied this methodology to the analysis of L-band satellite products. The objective is to characterize the salinity errors that we have in the different L-band satellite salinity products, and also to assess which is the best suite product depending on the location. We have for that 5 products, 3 coming from SMOS radiometer and 2 coming from SMAP, and we have estimated the salinity error of each product as the average of all the estimated errors from all the triplets where the product is considered. And as a metric of the uncertainty in the error estimation, we have computed the standard deviation of the estimated errors. Here I'm showing the mean estimated errors among the different triplets for the 4 datasets. The 2 on the top comes from SMOS and the 2 on the bottom comes from SMAP. I'm not showing here, but the uncertainty in these maps, in this estimation, is below 0.03 PSUs in all the products and in almost all the regions. And in general here, for example, we can see that the error, the lowest error is by SMOS BEC low resolution product. And this kind of information allows us to build this kind of maps, indicating which is the product with the lowest error. Here, for example, in the comparison of these 5 products, we can see that the most big low resolution product is the best one in the bulk of the ocean. When we look at the Amazon and River Congo plumes, the small big high resolution is better. In regions affected by RFI, of course, we can see clearly that the SMAP products present lower errors, and in the Southern Ocean, the CATDS product is the one with the lowest error. So, as a conclusion, this methodology, the correlated triple collocation, is especially suited for triplets of remote sensing variables that resolve similar spatial scales when we have very few data sets and not completely independent. And this method provides reliable estimations with a scarce sampling size. This technique has allowed the successful assessment of the global, in a global way, of the nodal sampling performance as an RFI mitigation technique. We are using it also for assessing the performance of the RFI mitigation technique included in the new version of the Small Cell 1 processor. This is an ongoing task. And we have also assessed the salinity errors of all the available L1 salinity products. And this methodology is currently being used by the SMOS Expert Support Laboratory as a metric for assessing the performance of the new versions of the processor. And it's important and it's very useful because you don't need to go to the geophysical retrieval and validating the geophysical parameters to understand the improvements and limitations of the changes proposed at level 1. So thank you for your attention.
Okay, thank you, Veronica. It's time for quick question. No questions, so we can proceed to the next one that is presented by Niels Skov. Future high-performance spaceborne microwave radiometer systems. Okay, Niels.
Just a minute. I'm going to enable okay, now you should be able to share your screen.
Yes. Well, I don't know where it starts at 2, but anyway, can you hear me?
Yes, we can see it. Yeah.
Okay, so I'll switch to something very completely technical. I'll talk about some high-performance new radiometer systems that are being considered presently. And the users of multi-frequency radiometry have been served for years with instruments like the AMSA type, and we already heard something about that, where you had something like 50-kilometer footprint at C-band at 20-kilometer at Ku band. But new ambitious systems are being studied now, where we talk about 15 kilometers at C-band and 5 kilometers at Ku band, and at the same time, which is of course very difficult, also better radiometric sensitivity. So we're talking about something that is at least 4 times bigger than we have seen so far. We are talking about antennas up to 7-8 meter range. And this poses some challenges, of course. Also, we need better receivers or integration of many beams to get better delta T. So I will consider an example. A completely traditional scanning system by a rotating antenna, which looks like here you have a large antenna and you have your receiver sound here and the horns here, and this rotates, and that's how you make it work. Nothing new there from the size. Quite a normal big altitude, so normal incidence angle on that. I just defined here exactly what I mean by footprint, because this becomes interesting in the discussion. I assume a 20% footprint overlap both across track and a long track to get the proper sampling. And then the example I'm going to talk about is shown here from C up to Ka band. Quite normal bandwidth. And here are the footprints I talked about, 15 at C band and 5 at Ku band, and very stringent requirements to the radiometric sensitivity. Now, what can we do about that? We put that into whatever we use. I use Excel to calculate it. Here's just one example, and you should not go through this table at any detail at Ku band. The interesting thing is here we have the footprint, and I want to go down to 5 kilometers, meaning that I get an 8-meter antenna. At the same time, I get this big antenna to rotate 77 times per minute, which is absolutely impossible, and I get a very, very poor delta T. So something has to be done. So there is delta T issue and an RPM issue. And the thing to do, if you just go ahead, is that, okay, we need many beams to integrate over. We actually need, if we want to fulfill all the requirements, 4 beams at C band, 6 beams at X band, 12 multiplied by 2, 24 beams at Ku band, and 20 beams at Ka band. This is, of course, a major challenge concerning feed horns and the receivers and all that. But then everything turns out well, only 6.5 RPM, which is quite slow. And I even only assume that we look either fore or aft. But we have all these many beams, and then, and especially if the high frequencies, as you see, many, many beams. And then, of course, you have to sit around the table with the users and the space agencies and discuss, is this possible from a technical or financial point of view? And such discussions, we have to realize that they are there. We can relax on the footprint overlap, then we get fewer beams. We can look both fore and after, maybe also get fewer beams, and there can be many other discussions. So in the end, you come to some kind of conclusion of what you can do. But still, of course, you have many problems. You can either use classical feed horns with receivers, or you can use the new thing called focal plane array systems. In the classical thing, you have a traditional receiver like that with a feed horn, calibration issues, and then just a receiver, amplifiers and stuff like that. And in this case, you then have 4 feed horns at C band. Let's take that example, and then 4 receivers. But I can also instead use a system with a focal plane array where I have many, many small antenna elements, and I add some of them to get one beam, some others to get another beam, up to 4 in this example. And the way this is done, if you are kind of stupid, then you have power dividers after the antenna beams and then power combiners before the receivers. This will not work, of course, because of the loss that you will get here. No, you have to go the full way, and that is here you have each and every of your small antenna elements. Each of them will have its own receiver and its own A to D converter. And bear in mind, you have to A to D convert the full bandwidth, many hundreds of megahertz, which is an issue, of course. And then you go into a large FPGA where you calculate the beams, in principle, as simple as you add the signals in amplitude and phase, and then you get optimal beam performance. So in such an array that we will consider here for C-band, we typically need to have 35 small antenna elements. That means 35, something like 35 receivers. This has never been flown. It has been demonstrated both theoretically and physically by a model on ground. So when you go to the space companies with this idea, they will say, quite right, there is a significant development risk, of course. Now, if you go to classical horns and single receiver, then of course you have a minor risk. A very important benefit of the focal plane array is that more beams does not require proportionally more antenna elements. So even the high frequency stuff with many, many beams does not require an overwhelming amount of antenna elements. And something I will not discuss here is that you get much better beam performance, but that's another thing. Now, small receivers can easily be made X-band and below. It's a little more challenging to make them at the high frequencies where not so much hardware is available. So a possible compromise is that you can have the focal plane array substitute and very practical compromise, substitute some very large horns at C-band, and then at the higher frequencies go the more traditional way. And this is what I will cover in this example. For instance, here at C-band, we need 4 traditional receivers, 4 traditional horns, which are quite large, as you see here. You see the measures here. And that can be replaced by this small focal plane array with something like 30 small elements, actually 35 in this case. Much smaller and lighter. What are the consequences of doing this? Well, behind each and every one of these small antenna elements, I have a classical receiver with some amplifiers and a mixer to mix down to the A to D converter, suitable frequency and stuff like that. And what I've done is then that I have simply taken very important commercially available components. I'm not talking about something fancy, things that we can dream of in the future, but this is what you can go and buy if you want to. I found the input switch. I notified the oscillator. I'll not go through all this. I see here the types for the different amplifiers and stuff like that. I found all these, and I have the properties of them spelled out even more. I have more frequencies here, but here we talk about C-band, so I know what is the noise figure and the losses and all that. And then I can make simply a design, and here is my very important design, a power budget for one parametric C-band system. One or receiver first. We need preamplifiers, we need some extra amplifiers, we need some IF amplifiers and calibration stuff. So in the end, I find out that I can make one receiver with only 370 milliwatts. Since I have in this case 32 channels, each of them dual polarized, so I need 60.
You have 2 minutes left.
Yes, I need 64 C-band receivers, 24 watts. Then I need 2 watts for the local oscillator, and then I need to buy 2 each very large and powerful FPGAs that can do all the sampling and the calculations. They require 40 watts. So the combined system of such a C-band will require 66 watts. And what can I say about that? Well, of course, this is more than we are used to in radiometers. But on the other hand, radiometers have always been the very, very nice guys in the shop, requiring very, very little power. And you know that nowadays you can make satellites that require that can provide much, much bigger power than this. This is simply not a showstopper. And to come to the conclusions, the focal plane array has a lot to offer for next generation systems. A cluster, for instance, a very practical thing, a cluster of very large C-band and even X-band horns you might consider also can be replaced by a small focal plane array. By the way, you get superior beam quality, but that's another stuff. I haven't covered that here. The price to pay is no heritage and slightly increased power consumption due to the many receivers. But as I said, a fully parametric C-band focal plane array system will only consume 66 watts, bearing in mind buying straight away already available components. If you, as a space company, go to some of these providers and say, can you try to optimize the power consumption, I'm sure they can make it even better. So this is a nice way that we can solve some of the problems for the new advanced systems. And I guess that's what I had to say.
Okay, thank you, Nils, for this presentation. We have already a question. When you say you must a 2D convert the whole bandwidth, how wide must it be? Just the bandwidth of interest or much wider?
Well, I don't know if I understood your question well, but since I want to actually add the representative fields of each and every of these antenna elements, then of course I have to take the signal with amplitude and phase and add them just as I could have done in principle. What I do electronically here is what I could do in principle by MicroRad components here, but this just won't work for a radiometer because of all the losses you get in this MicroRad circuitry. But I do nothing else in principle here than what I do here. But the cost is that since the radiometer signals are 200 megahertz wide, then of course I have to A to D convert these 200 megahertz signals to get the proper signals to add.
Okay, Giovanni De Amici, my question was, you need to convert the 200 megahertz, but you don't need to go outside that band.
No, I don't need to go out. I need to convert it properly, of course, with a sampling frequency that is twice the bandwidth, whatever that is. So if it's 200 megahertz, then the sampling frequency must be at least 400.
Okay, thank you.
Okay, any other question or comments?
I have just a very small curiosity. Thank you, Niels, for your very interesting presentation. Do you think your idea could be applied also to L-band antennas? You know that now there are two opposite techniques currently operating, the SMOS with the antenna array and the SMAP with the large umbrella reflector. Do you think?
Of course, this can very well be done at L-band. We have already considered that a lot, and we actually made a proposal for EE 9 or 10 or whatever it was a couple of years ago with a full, not a full design, of course, but you know how much design you have to do one of these Earth Explorer missions. So this can be done very well at L-band also, absolutely.
Okay,
at the
thank you very
L-band,
much.
the benefit of getting rid of the horns is, of course, overwhelming in the sense that an L-band horn is the size of a full paper bucket and stuff like that. So,
sure,
an L-band.
Okay, thank you very much.
Okay, other questions or comments? No, so we can move to the next presentation. That is from Matteo Alparone, enhancing the spatial resolution of radiometer data using a multi-channel prism technique.
Okay, hello everyone. I'll now proceed to share the screen.
Yeah.
Okay, can you confirm the screen is okay?
Yes.
Yeah.
Okay, thank you. So I'm Matteo Alparone from University Partenope of Naples, and this work is entitled Enhancing the Spatial Resolution of Radiometer Data Using a Multi-Channel Fusion Technique. So here you can see a basic outline of the presentation, which will consist in an introduction on inverse problems, a theoretical background, the description of the new approach we are proposing, some experimental results, and then some conclusions. So as we know, inverse problems are interdisciplinary and are involved in several fields of physics and engineering. Here, for example, seismology, medical tomography, or remote sensing. Here we are focusing on microwave remote sensing, so techniques used to measure electromagnetic scattering or emission from Earth's atmosphere using satellite or airborne instruments. In particular, how does it work? The physical properties of the region of interest affects the electromagnetic properties. So thanks to remote sensing, we can infer information on geophysical parameter we are interested in by mapping the electromagnetic properties. In particular, the microwave band has all day, all weather usability, so can penetrate clouds and do not rely on the sun as a source of illumination. The main drawback of the passive microwave remote sensing is the intrinsic low spatial resolution. This means that it's adequate for many global applications, but it suffers when passing to regional studies, for example, coastal zones monitoring. So when we are dealing with these regional studies, resolution enhancement algorithm has to be invoked to provide improved resolution images. In particular, they provide this resolution, these improved resolution images by taking advantages of the oversampling. As you can see on the bottom left part of the slides, for example, we can provide, while here we can see the measurements, for example, of the SSMI microwave radiometer, and we can provide resolution enhancement by enhancing the spatial resolution and producing the image on the underlying rectilinear grid. From a mathematical point of view, we have to deal with a linear system, which is AX equal to B, where A is the matrix that describes the projected antenna pattern, X is the unknown brightness temperature to be retrieved, and B is the measured antenna temperature. So image reconstruction methods we are dealing with attempt at inverting this linear system to retrieve the brightness field on a finer spatial grid. In particular, when we are dealing with this kind of problems, as we say, the linear system is ill-posed, but in particular, it is undersized because, as we said, we are trying to infer the image, the brightness temperature we want to retrieve on a finer grid. So there is a non-injective mapping in the system. This means that if we have a reference field, for example, this one shown in the bottom left part of the slide, if we take the projection of the reference field on the kernel of the system matrix, we see that what we see in the kernel parallel projection is the information we are going to lose when inverting the system. There is no way to retrieve this information. And in particular, in this case, we can see that is the borders information of this abrupt discontinuity, this pulse function shown as reference field. So in this first simulated example experiment, we have this reference field, which is a 300 Kelvin pulse function. With the forward problem, we obtain the simulated radiometer measurements we can see on the top right part of the slide. And we make the first reconstruction using the conventional Landweber method, which is the most classical iterative regularization technique. The key idea of the modified Landweber technique, which we are proposing in this study, is to use the kernel parallel projection as initial guess for the method. In this case, as you can see in the red box, the results obtained with this method are way better than the one obtained with the conventional Landweber, since we are recovering the lost information by initializing, as you can see in the X0, we are initializing the regularization algorithm with a projection of the true brightness field onto the kernel of the forward operator. So with this technique, in the noise-free case, we expect to recover the full information, while in the noise case, this is not possible. We are getting very good results. To provide a deeper analysis, here we show the horizontal and vertical transect. And as you can see, the modified technique we are proposing, which is the green line, is getting very better results. Well, of course, here we were talking about simulated experiments with a reference field, but in real practical case, we don't have any reference field. So we need to approximate somehow this reference field. For instance, our idea was to use the measurements collected by a finer resolution radiometer channel and use it as a reference field, under the assumption, of course, that the spatial information is highly correlated with the lower frequency channel. Otherwise, we get something that is not fair. So in this use, for example, we will use, in this study, we will use the spatial sensor microwave imager, SSMI, and in particular, it's 19 gigahertz and 37 gigahertz channels. So we will take this 27 gigahertz channel as a reference because it's, it has intrinsic higher spatial resolution, as a reference field for getting the additional information as initial guess. So here you can see some actual measurement, which is an SSMI image over part of the United Kingdom, Ireland, Northern Europe, and Scandinavian Peninsula. As expected, the lower frequency channel is characterized by blurred edges and coastlines are not well defined, while in the higher frequency channel, the 37 gigahertz, the coastlines are better visible, and also the edges are better visible. So if we try to use our technique, since as I already said, since the true reference field is not available, we are using as initial guess of the iterative regularization algorithm the higher frequency channel. What we can see in the results is that we obtain with the modified Landweber technique a better reconstruction of smaller targets and reduced signal fluctuation. In particular, in the top transect, you can see that the Isle of Man, which is completely wiped out in the measurements and using the conventional Landweber, is again reconstructed and is very well visible in the results obtained by the modified Landweber method. And in the second transect, you can see that we have reduced fluctuations. So these are the two main results with this experiment. Here you can see a second real case experiment, again with some SSMI actual measurements, this time collected over the Canary Islands. As you can see in the 19 GHz channel, the measurements are has the islands that are very blurred and the coastline is not well delineated. So to better quantify the improvement obtained with the modified Lambert technique we propose in this study, we have two zoomed in. The first one in the red box comprises 4 islands, which is La Palma, Tenerife, Gran Canaria, La Gomera. As you can see in the 37 GHz in the higher frequency channel, we can see clearly 4 islands, while only the blurred version of only 3 islands can be observed in the 19 GHz case. As you can see, the LV conventional Landweber method results has no signal hints related to the small island, which is La Gomera in the southern part, while the results obtained with the modified Landweber has clearly some hints of the small island. The same results are obtained in the green box where we are seeing the El Hierro Island, and we can see that with the modified Landweber technique we are proposing, the structure is better delineated with respect to the conventional Landweber. This analysis...
Okay, you have 2 minutes left.
Okay, thank you. So this visual analysis is also confirmed quantitatively by the correlation metric, which is in the table in the left bottom part of the slide, which is calculated this correlation with respect to the higher resolution channel. So we can see that in both cases, the modified Landweber method we are proposing is getting better results with respect to the conventional Landweber in the case of these small targets. So in this study, we propose a new method, a new Landweber method, and its key feature is that it can restore part of high frequency details related to reference scene that are completely missed out by canonical Landweber methods. As we have seen, the experimental results confirm the soundness of the method, in particular when restoring small hotspots or reducing the ripples on the reconstruction. Of course, we have to take into account that a factor that limits the application of this particular method is the difference in terms of brightness temperature behavior, because if we are using a channel which has different frequency but has a different brightness temperature behavior, we risk to introduce some hints about geophysical parameters which are not of interest. So this is the factor that limits the method. Thank you very much for your attention.
Okay, thank you, Matteo, for your presentation. Are there some comments, questions?
If there are no other questions, I have a couple of comments for Matteo.
This is Marian Klein. Can you guys hear me?
Yeah, I can hear.
Okay, so all the plots that you were showing are assuming that the footprints from the radiometers that you are combining are looking through the same atmosphere or clear atmosphere, just looking at the surface parameters, right? So what would happen to your method if you have like difference in the atmospheric properties between 19 and 37 gigahertz, as you were showing?
Yeah, no, this would be a serious problem because it would introduce some unwanted signals. So this is a good point. This is another factor that could limit the method.
Thank you.
I have a question, if possible.
Yes.
Yeah.
Okay. Just so, as far as I understand, that this method needs some overlapping of the footprints of the radiometers.
Yeah, sure.
So, in principle, it cannot be applied to the L-band like SMAP, I assume, because in that case, there is a very limited overlapping of the.
We have done some experiments, and when the overlapping is also we are using here the 37 gigahertz. Also in the 37 gigahertz of the SSMI, the frequency, the spatial resolution is higher, but the overlapping is very limited. So we have done some experiments, and when using this kind of method that relies on overlapping in this kind of situations, the results are not good. because we have too few information. As you can see here, we have 3 kilometers linear overlapping in the 37 gigahertz. That is not enough to get a good reconstruction.
And the last question, did you try to compare it with other methods for improving the spatial resolution, like the conventional Backus-Gilbert technique, or also the smoothing filtering based modulation technique?
Yeah, okay, sir.
Please go ahead.
Sorry. No, not in this study, but we have other studies where we compared the canonical Landweber with the Backus-Gilbert, and assuming that, well, in the Backus-Gilbert there are more parameters to set, but the results are more or less the same. So when we are comparing to the canonical conventional Landweber, we are comparing somehow also to the Backus-Gilbert. So the Backus-Gilbert should be the reference with respect to Landweber, and here we are getting some better results with respect to the Landweber, and I guess with respect to the Backus-Gilbert.
Okay. Thank you very much.
Thank you very much.
Okay, other questions, comments?
Nothing from YouTube, Simone.
Okay.
If there is some time left, I can add one more.
Sure,
I apologize,
sure.
but know, we have developed the smoothing filtering based intensity modulation to disaggregate 10 years ago, if I remember correctly. To disaggregate the FIM, and now is employed in the LPRM retrieval algorithm for solid moisture from AMSTAR 2. So did you try to compare with this? Is a personal interest, of course, and I apologize for advertising in this case, but
no, I never tried, but it could be interesting. So thanks to the.
Yeah. Okay.
Yeah, we plan to do it. So thank you for the comment.
Thank you for your answer.
Okay, so if we don't have any other question, I should move to the next presentation. That is from Ignasi Corbella. Ignasi, can you
just a minute?
Yes, I'm here.
I'm giving you the ball. Okay, now you should be able to share your screen.
He's going to present digital IQ demodulation for interferometric radiometers.
Yeah. I hope you see my screen.
Yes.
So this is a work about the digital IQ demodulation for interferometric radiometers that I will present. My name is Ignasi Corbella from Politecnic University of Catalonia. And on behalf of my co-authors, Manuel Martinera from the European Space Agency, José Vilaseca and Albert Catalán from CENER in near Barcelona, Spain, and Francesc Torres also in Polytechnic University of Catalonia. The contents of my talk today would be start with an introduction, then explain how is the digital IQ demodulator, show how we have developed a demonstrator for this technique, and some experimental results about this demonstrator, and I will conclude with some conclusions. So that work is in the frame of SMOS. SMOS follow-on operational mission. You know that SMOS has already 11 years of life, so that at some time there will have to be some replacement, and we are making a large effort to make operationally feasible some follow-on work. So in this frame, a new instrument design has been proposed, which is based on the lessons learned from these MicroRads. In order to reduce the hardware complexity for this new receiver, the digital in-phase and quality modulation is considered instead of using just the analog IQ. In this schema, I and Q components are obtained by multiplying the digitized IF signals, or signals are digitized in IF, I multiply it by a digital local oscillator, and then afterward filtering to the output. Then the purpose of this presentation today is to analyze this concept for its use specifically for this application of interferometric radiometry. This technique has already used in some other areas, but for interferometric radiometer, it's quite novel, and provide, of course, some experimental results. This is basically the conceptual block diagram. We have for one receiver, the left part, the IF. Here we have a signal centered about center frequency of 0, then ADC, and then digital IQ mixer. That means they're multiplying by a cosinus here and a sinus, a minus sinus here. And that if we choose the sample time for a quarter of a period, then the cosinus is 1, 0, minus 1, 0, and the sinus is 0, minus 1, 0, 1. So this, in the end, has to be filtered out. And this schema basically what has is selecting this branch or this branch because depending on the clock. If we analyze this block diagram, we end up that with two receivers, we have I1 and Q1, and then the average of this product is basically the average of this product of this signal here at the same instant, and the QI, which is the imaginary part of the correlation, is the average of the signal, and the other one delayed one clock. So in the end, we can re-draw this schema, and what we are doing, in fact, is this. So the IF for one receiver, the IF for another receiver, a sampler, and with the clock, and then just one signal as it is, and the other one as it is also. The correlation gives the real part, and then one of the receivers is delayed one clock, tau equal to T0/4. In terms of analytic signal, that means that multiplying by minus J. So in this case, we multiply this from this, we obtain something that is proportional to the imaginary part of the correlation, with the correlation effect due to the delay is not exactly Hilbert filter. It has some decorrelation that has to be taken into account in the imaginary part. But this is feasible perfectly. So digital IQ emulation is implemented by delaying one clock the output of one receiver with respect to the other. The real part is the cross correlation of the average product of two non-delayed signals. The imaginary part is the average product of one delayed signal with other one non-delayed signal. Then, if sampling frequency is 4 times center frequency, then for a narrowband signal, this schema provides approximately the correct complex correlation that we are willing to measure. Of course, the sampling frequency is fixed for hardware, and then the center IF frequency may vary as a function of what is the filter we are using. So actually, in practice, we have some center frequency error because the center frequency of the filter cannot be exactly the 4 times sampling frequency divided by 4, but this is an error that can be corrected by processing. And the imaginary part suffers from the correlation, but also this error can be corrected by processing. The demonstrator we have built is an IQ emulation for the advanced receiver for future L1 radiometer, which is a project which is developed by CENER in Spain under the ESA contract. There's dual polarization receiver, H and V, at this frequency with this bandwidth, single frequency conversion with this LO, this intermediate frequency, sampling frequency, which is 4 times the intermediate frequency, 150, and the Q signals are obtained by delaying one clock the IR signals. So no analog mixer is provided. The test bench uses two different LRs. LRs is this, that are driven by correlated noise, provided by a single noise source and a power divider. There are 11 levels of noise, and within each LR, input power is further divided into both horizontal and vertical. Then there's a 1-bit 2-level correlation products between all the output signals, and also including the self-IQ for each one. Amplitude is measured by a power measurement system implemented in each. Then this is the measurement setup. The noise source, 11 levels divided by 2, and then the 4 signals, EMS, and correlated to the measurements. The sampling strategy for II, we have this signal and this corrected with this one at the same time. For the QI, we have this signal corrected with this one delayed one clock. QQ is basically the same as II, both delayed, and IQ is just delayed one, this one with respect to this one. So using this schema, we have built these demonstrators, and we have analyzed all the different correlators. This is the result for the self-IQ correlator, which is related to the center frequency error. This self-correlation for each of the 4 receivers is this one is not 0. It will be 0 only if the intermediate the center frequency is a quarter of the sampling frequency. So there is a center frequency error, which is this one here. The center frequency is the sampling frequency divided by 4 minus some error. The error measured here with this method is for these 4 receivers, this one here. So this is the nominal value of the IF. This is the estimated value of the IF for these 4 receivers, which is quite consistent with the expected center frequency. And this is the cross-correlation amplitude that is measured between any pair of receivers, H1, V1, H1, A2, and so on.
Yeah, you have 2 minutes left.
Okay, so this is in lines is the actual measurements, and the circles are the theoretical computation computed from these parameters of the noise distribution network and from the temperature. You see that there is perfect match between the theory and what we are measuring in this with this schema. This is the difference in correlation units of this between measurement and theory. And this is the same for the phase. We see the phase very linear, very constant, I mean, and with a very small error along the power. And finally, we have measured what is called the front washing function shape by delaying 2 clock more the one signal 1 and signal 2. So in this case, by delaying one signal with respect to the other, we are able to compute the cross-correlation of this point and this point at 0, and then obtain the fringe washing function from all these 6 baselines in amplitude and in phase. Ideally, this should be flat, it has some slope, and ideally this should be maximum at 1. These are the approximation of the fringe washing function for all the parameters A, B, C, and E. That corresponds to this approximation. And for example, the C parameter corresponds to the delay with respect to the one receiver with respect to the other. This is the frequency error, and this is the bandwidth. The bandwidth that is measured with this technique matches perfectly well with the bandwidth of the signal. So as conclusions, the digital IQ emulation simplifies hardware, but has an important impact on the way correlation measurements are interpreted and processed. 2 new errors appear, center frequency shift and the correlation of the imaginary part, and both can be corrected using new formulation. Measured results in ILR confirm the feasibility of the proposed processing. We have obtained consistent center frequency errors, amplitude and phase of correlation, and fringe washing function shape. And that's all. Thank you very much for your attention.
Thank you, Ignazio. Question or comments?
Ignacy, I have a question. Al Gashevsky.
Yeah.
Very nice idea. Very clever. But I wanted to just check. It seems that you have to have the A to D converter sampling at twice the usual Nyquist rate for this. Is that correct?
We are sampling twice Nyquist, yes. Mm-hmm.
So there's a little bit of a drawback. I think it's a minor drawback, but it does require a little faster sampling.
It requires faster sampling, yes. In this case, we are sampling at one. This is the this is the sampling frequency, 115.
Yes. Oh, great. Yeah, 4 times. Okay, thank you very much. Very good.
Could I, Sten Saustrup, could I just ask a clarifying question on Al's question? Does it mean that the bandwidth that you reliably get through is sort of half the Nyquist sampling bandwidth, and the degradation is what you can live with if you have sort of a relative bandwidth of 0.5 compared to full bandwidth for Nyquist sampling?
Sorry, I didn't get exactly what is the question. Sorry.
Well, you need to sample at twice the Nyquist frequency.
Yeah.
So is the degradation of the 4 Stokes reasonable if you just stay below, say, 1/2 of the Nyquist bandwidth?
No, the idea is we have to sample at this frequency because it should be 4 times the center intermediate frequency in order to recover all the correlations. In order to minimize the center frequency error. This is the way it works. Yeah.
Yeah, I understood that. That's you sample sort of 4 times the intermediate frequency or the center frequency of whatever signal you have. But how much relative bandwidth can you have before the imaginary part degrades beyond reasonable levels?
Yeah. I understand. Yes. It is basically this degradation here. This is the sync the b tau basically. So this is the sync function of b with times t0/4. So if the bandwidth starts to increase, then this goes to 0, and then it can be a problem. Yeah. It can be corrected, but of course the errors, if larger, are very more difficult to correct. But if we know the frequency function, because we know the bandwidth, we can use it here to compensate this the correlation here. But of course, if the bandwidth increases, that doesn't work.
Okay, you can continue.
Thank you.
The discussion online also. Okay, I should leave my role of chairman to Niels.
Okay, so my name is Niels Skov, and I will take over now and keeping track of everything. So what we are going to hear about now is Eric Anterieu, and he will talk about synchronization of radar signals in this new fancy L-band interferometric system that we also heard about yesterday. Can we have Eric Anterieu coming up? Yes, he's coming.
Yes, I'm here.
Yeah.
Good. So, you can see my screen?
Yes.
Thank you. So this work takes place in the long story of the global L-band measurement started by SMOS 11 years ago. Within the frame of the studies conducted by CESBio and CNES for the next generation of imaging radiometers, ULEAD plays a key role in the roadmap because the capability to perform unconnected interferometry in space is one solution for improving spatial resolution up to levels that cannot be reached with connected interferometry alone. The challenge is summarized here with a 2-element interferometer observing the Earth. The correlator output is the so-called visibility, V, which is nothing but the degree of spatial coherence for the baseline vector B between the 2 antennas. Each branch is equipped with front-end and back-end elements. RF signal is mixed to an halo to produce IF signal. As the two branches are not physically connected, the IF signals are digitized with a clock of each halo. Then they are sent to ground where correlation is performed at a later time. To fix numbers on IDs, here are the frequency bands involved. The down conversion from RF to IF is performed with this local oscillator frequency. The brightness temperature distribution seen by the interferometer is discretized with pixels behaving like black bodies following the Planck law at temperature T. The RF signal collected by an antenna with voltage pattern F is nothing but the sum of these contributions when accounting for the flying times tau between the pixels and the antenna phase center. As the Earth and the instrument are moving in relation to one another, flying times continuously change, and consequently, Doppler frequency shift of few kilohertz is expected. Here is an example of RF signal kept by one antenna. As I just said, the poor spectral density follows the Planck law, and in addition, in the time domain, real and imaginary parts follow a Gaussian distribution. In unconnected interferometry, the radio signals received by pairs of antennas are sampled and recorded with an accurate time base provided by an atomic clock. At a later time, at the location of a correlation unit, they are synchronized before being combined. ULIT cannot embark an atomic clock. Another solution has to be found. The requirement for the relative timing is 10 picoseconds, the equivalent of the 3 millimeter for the baseline accuracy. The solution cannot be brought by GNSS receivers because the accuracy of their clock is only about 10 nanoseconds. The solution proposed here is to use the signal sent by a radio beacon emitting in a band that is as close as possible to the protected L band, so that this signal will travel through the same front end as the signal from the Earth up to digitization. At IF level, the signal is split in two components. One pass for the beacon signal devoted to the estimation of the delay between the two branches, and the other one for the Earth signal. To fix again numbers on IDs, there is a service band here in green from 1427 to 1429 MHz that is close to the protected L band here in red. The radio beacon will emit a periodic signal in that green band. Although emission is permitted in the service band, as the L band is protected from any emission, there are some rules to respect. The ECC has limited the level of unwanted emission power in the protected band to 36 dB below the passive emission in that band. The shape of the RF signal emitted by the radio beacon in the service band is inspired by the level 1 GPS signal. PRN codes are pseudo-random noise codes or gold codes with the property of having a narrow self-correlation and close correlations close to zero. Here, the gold code number 37 is used, and the level of the emission is controlled with a raised cosine filter. Here is an example of an RF signal emitted by a radio beacon and kept by one antenna. Real and imaginary parts do not follow a Gaussian distribution, of course. Here is an estimate of the power spectral density, showing that the emission from the radio beacon in the service band in green does not exceed what is imposed by the ICC decision in the protected band in red. More exactly, the level of the RF signal from the beacon is 17 dB above the Earth emission in the service band, while it is about 40 dB below it outside the service band, including in the protected band on the left. With regards to the power transport by this signal, I just want to focus on the contribution of the beacon to the average brightness temperature, which is less than 0.102 millik compared to the 147K for a typical scene. The algorithm for the synchronization is based on time correlation as they are performed in the lock loop used in GNSS receiver for pseudo-range estimation. The RF signal emitted by the beacon is compared at IF level to a reference signal generated locally. The delay between those two signals is estimated in two steps. For a pair of antennas, the delay between the beacon's signal kept by the two antennas is deduced from a simple difference. Here is an example of the first step, the acquisition. Here for the first antenna, and there for the second one. This first estimate of the code delay and the carrier frequency are obtained from the very first millisecond of signal, which correspond to one full PRN code. In the second step, the tracking, the IF signal from the beacon is analyzed every millisecond at the rate of duration of the PRN codes. On the left is the evolution of the code delay, and on the right, that of the Doppler frequency shift for the first antenna, and here for the second one. These estimates of the code delay obtained at the rate of 1 millisecond are finally filtered to reduce time variation shorter than 0.5 seconds. The difference between these two filtered estimates lead to the estimation of the delay between the two branches of the interferometer and shall be used at IF level for synchronizing the emission of the Hertz scaled by the two antennas. After processing 30 seconds, the final accuracy is better than 2 picoseconds, and the 1 sigma uncertainty is less than 10 picoseconds. The same estimation has been performed with the beacon signal processed in the time reversed order to reduce bias that may be linked to the direction of processing. The same level of accuracy and uncertainty is obtained. Here again, we can observe outliers when the sign of the Doppler frequency shift swaps. In addition to this homemade approach, the GNSS software has also been used to comfort the solution of a radio beacon used for synchronization. Although the approach is also a two-steps one, this kind of software takes benefit from many years of experience in GPS signal processing. However, few parameters have to be adapted to the frequencies and bands of ULEAD, which are not those of level 1 GPS signals. Preliminary results are very promising and obtained in a shorter processing time. Moreover, GNSS signals simulated with a Skydale hardware generator have been processed with success. To conclude, the accurate synchronization of radio signals at IF level is a strong requirement for unconnected interferometry. For ULEAD, a solution with a non-directional radio beacon emitting in a service band close to the protected L band has been proposed and studied. Preliminary results have proven that 10 picoseconds of accuracy for the relative timing is not a dream. Thank you very much.
Thank you, Eric. As usual, you are behaving very well. So you just finished on time, and there's time for questions. And remember that you are actually allowed to switch on your microphone and phone and ask them by talking. Any questions?
Eric, good afternoon. This is Manuel. So how do you solve the problem of visibility of this ground beacon from the constellation of small satellites?
I'm sorry, I didn't understand the very beginning of your question. How do you?
Yes, the visibility, unit visibility of the ground beacon from the constellation of small satellites. But so you need several beacons around the world. How do you solve the problem of visibility?
Right now, we are just studying this possibility for ULEAD. For ULEAD, we will have only one beacon, and one of the objectives of the mission is to check how long we can keep the synchronization with the information acquired over one beacon. And only after having this information, we can decide how many beacons we need to have a full coverage over the Earth.
Yeah, Thank you.
So, other questions, please? There doesn't seem to be anyone on the chat, so...
No one also from YouTube? No, they didn't. Just arrived a question. Just a second. I'm transferring it. Okay, I just transferred the question from the YouTube chat.
Oh.
Would it be possible to put the beacon on the main satellite, which could possibly house on clock? This is the question.
Yes, it is, provided that you have a perfect knowledge of the position of the beacon with respect to the other satellite.
Okay.
Okay, other questions? Well, then maybe we should just move on, because it also takes a little time to go from one speaker to the other.
Yeah.
And the next speaker is Janne Lahtinen, and he will talk a little bit about a refurbishment of the HUDRAD system. So can you put on Janne?
I should have enabled you to share screen now.
Yeah, he's coming on.
Can you see my screen?
Yes, we see your screen, and we see your nice image now. So
okay.
I think it's fair enough that you can start, because it's almost time in a few seconds.
Okay, thank you for this extra time, and hello everybody. My co-authors in this work represent several organizations: Finnish Meteorological Institute, Aalto University, and two companies called Mobalean and Nuolelento. And this work was financed by ESA, the FMI, Meteorological Institute, being the prime contractor. And the motivation of the work was that for the SIMREX campaign, to support the SIMR mission, a radiometer was needed to perform measurements in Arctic region that would have frequencies that happened to be the same as a legacy instrument called HUDRAD. HUDRAD was developed in mid-90s and extended and modified also during the 2000s. But this system was quite outdated. It was developed for, let's say, as a student project or for master thesis and so on. It has been used over a long time for scientific measurements, but it already had some major and minor malfunctions. Also, it was developed for different aircraft that was available for this measurement campaign. So refurbishment was needed. And here you see two pictures of the original profiling system. It included two systems, high frequency system that incorporated frequencies from 24 to 90 gigahertz, and a so-called low frequency system that incorporated 6.8, 10.65, and 18.7 gigahertz dual polarization receivers. As you can see, it had three parabolic antenna that would be very difficult to accommodate in a Twin Otter aircraft, to say impossible. So this was one thing that needed to be modified along with the malfunctions. Here you see a low frequency system from backward. These are now installed in a short Skywan aircraft that was originally used for these instruments. And here you see 3 different receivers in the boxes, and also at the designated as D is the so-called control processing unit that generates the secondary voltages and controls the instrument. Here's a schematic how the extent of this refurbishment. So with red, the new parts and subsystems are designated, and repaired and modified subsystems are designated with blue color. So first of all, we needed new antennas, then a new mechanical frame, also enclosures were new. Actually, in the receiver side, the only thing that we used were the old RF components, with the exception of switches that were broken and antennas, as said. In the control processing unit, we could use quite much, but we needed to change the broken parts and also make some modifications. The control software was quite interesting because it was, say, developed in the 90s, so it was made for DOS operating system, or it included DOS operating system. It also included novel server, so something that not many can master nowadays. We had the luck that we could incorporate in the team several engineers that participated in the original HUDRAD development. So it was sometimes like Space Cowboys movie that old farts are moving in again. Also, we incorporated in this system UPS that was not part of the original HUDRAD. And here's first a CAD picture on the left that shows how the system was designed, and a photograph of the assembled receiver. This is the 18.7 gigahertz receiver. You see that it's not very much miniaturized. So nowadays with modern components, you could make it much smaller. Of course, the antenna is what it is. But one of the problem in the project was, or challenge, that we had a very limited time for development. So we had a little bit more than half a year from start to delivery, and quite much time was reserved, or quite much. Our time window was also limited due to the lead time of the components, the switches and the antennas themselves. It's a photograph of the whole new system. So on the right side, there are the 3 boxes for the receivers, the frame that keeps them in the right position. This frame was then qualified for flight for aircraft. Took also some time. On the left side, we have the control processing unit, and on top of that is the UPS, and then the computer that incorporates the user interface and collects the data and stores them and so on. We measured the radiometric resolution of the old, new system, and also compared the results with the results obtained in the mid-90s by Kimmo Rautiainen in his master thesis. And we noticed that the delta T's have changed somewhat. Assuming that this change is only due to the change in the front-end losses, we see that 18.7 and 6.8 gigahertz have increased in front-end loss, whereas the 10 gigahertz channel has improved in performance. There are 2 potential explanations for this. First of all, in the original system, very high quality Digger switches were used, and within this time frame, we couldn't find anything in the market that would give the equal performance. And second, the antenna is different. So in the original system, we had parabolic reflectors with feeds, and now we had lens-loaded horn antennas plus an OMT, which may generate some higher loss. We tested the temperature stability of the system by bringing it into a cold room where we could generate different external temperatures, and we cooled the system or the external temperature to approximately minus 20 degrees centigrade, and then oscillated a little bit, and we see that it's not rock solid inside temperature, but this is pretty good. So the peak-to-peak variations in the internal temperatures are in the order of 0.1 degrees centigrade that we deemed was satisfactory. We see an installation in the aircraft, in the Twin Otter, before the campaign. That was in Svalbard. So we have here the receivers. They just fit inside the cargo bay. From our point of view, there is too little space, or the door is too small. Or you could say the antennas and the boxes are too big. On the other hand, we had requirement for the spatial resolution, so it was a kind of a difficult trade-off. And here in the cabin, we have the CPU, the control processing unit, and the control computer for the operator. To summarize, this legacy HUDRAD low-frequency system was refurbished successfully for the Simrex campaign. The tight schedule was a challenge, but it could just be met. We expected to restore the original performance of the system. Of course, because we used the same old RF components, we didn't expect to improve much. And in the Simrex campaign itself, the system worked without any anomalies. And this concludes my presentation.
Okay, thank you. Right on time. So we have time for questions. And remember, you can just ask them. No on the chat as far as I can see.
Hey, Yanni, this is Marian Klein. I have a question. How do you, when you have this installation in the aircraft, which was on the previous picture, is there a window that covers those radiometers? Is there a radome between the antennas and the cargo door?
No, negative. There is no door.
Oh, okay. So okay. So they operate basically in a slipstream.
Yes. That was one challenge for the design, and compared to the old system, we included some heaters inside the boxes. The original HUDRAD was not designed for these low temperatures in Svalbard. It's quite normal to have a minus 20 or even colder. So this is the upgrade we did.
All right. Do you have any other concerns with the antenna pattern when you have them inside of the aircraft like that, or?
Yes, I mean, of course, it is a concern that the antennas are so close to the metal walls. We didn't have a means to really simulate the system because antennas were provided by an external company or commercial supplier. Also, we didn't have much time to make system level tests with the aircraft before the campaign.
Very good. Thank you very much.
Well,
looks nice.
I can comment on that with the antennas, because we have here at our university done a lot of work like that also. And if you think about the first frontal zone, within that, then the antenna beam is almost like in a cylinder. So I don't think that this is going to be any problem when they're mounted that close to the door.
This was also my assumption. I think based on a discussion we had earlier, but I haven't discussed this in detail or researched myself, but I have got some information from the data analysis team that there is something going on.
Okay.
Some biases.
Okay, we have time for another question if there is one. Okay, if not, then thank you for a clear presentation and sticking quite to the time. So we have
thank you.
Without getting sweaty. So can you release Janne, and then we switch to actually one of the hosts, to Marco, who will tell about multi-channel radiometric correction for TOA brightness temperature for the effect of the mesh reflector.
Nils, the presenter is Ada Bosisio.
Okay, I'm not told. So,
okay.
Does anyone want to present this paper? Then carry on.
Okay. Do you see my screen?
Yes. Yes.
Okay.
You should just enlarge your picture so that you go into slide mode.
Okay. Is it good? Yeah.
Yeah. Oh, yeah. Okay.
Okay,
fine.
that's great.
Yeah.
Okay, I can start.
Yeah.
Okay, thank you so much. So this presentation addresses some technical and scientific challenges that arise during the phase A1B of the CMR mission, which is founded by ESA, one of the 6 high-priority candidate missions. This work was done with some colleague of my institute, the listed colleague of the CNR Institute in Florence, and with the support of OHB Italia as an instrument prime. Work are still in progress, and a great leap forward will be done during the phase B2 of CIMRA. Then in my presentation, I talk about an introduction to the CIMRA objectives. Then I will talk briefly about the antenna system characteristics and their effect on the antenna, on the measurements. Then our proposal to counterface this effect, our compensation algorithm. Then I draw my conclusion and the way forward. As we all know, the main drawback of sorry.
No, go on, Ade.
What happened? May I continue?
Yes, I
Okay.
had no problem. I think you should just continue. Someone said something. Continue.
Okay. So as I was telling, the main drawback of spaceborne radiometry is the achievable spatial resolution. This is crucial as Copernicus aims at providing, SIM in particular, aims at providing high spatial resolution of both measurements and the right product in the Arctic region. And specifically the observation of the regional sea area in the Arctic region needs a finer resolution to monitor many characteristic parameters, one for all the sea ice concentration, which can help in life of the people living in the Arctic area, of course, have an impact on the climate change. Then the CIMRA instrument will be the first one to cover a very wide spectrum from AL to Ka band, and with a final resolution, something about 1,900 kilometers, with a daily revisit time over the entire globe, and no hole at the pole. this factor lead are very challenging, and to have this kind of coverage, the only solution is a conical scanning with a rotating antenna assembly composed of one reflector, a various feed cluster from 4 to 8 for each band, just to have no gap in the gapless acquisition. And constraint in terms of mass and volume pushes toward a solution that foresees a deployable mesh reflector with about 7 meters of diameter. Of course, mesh because of the mass. The point is that such a solution introduces a gain reduction, and the most important effect is the presence of the grating lobe in the radiation pattern. Just to show you what happens, these are some sketches of the antenna projected on the ground in over the Greenland area, for starting from KU, KA, and KU band. Just to have an idea, the contour plot refines values between -3, of course, the footprint, and -50 dBs. And we have this area is something like 230 kilometers per 350, which is a very, very huge area. And even if grating lobes, some of them are as small as shape, they are many of them, and so the contribution in the error of the acquired temperature may be important. And I haven't said yet, but I say you later also, the requirement of SIMR is to obtain an acquisition near the coastline or this transition that is less than 0.5 Kelvin. So which such a kind of projection is a very challenging requirement. If we go lower in frequency, X band, a C band, of course, in C band we do not have grating lobes, but we have some of them in X band. They are very, very far, because here the geographic area is almost the double of the previous one. So we are talking about 700 kilometers, and those grating lobes, even if they are large in geometry, they are acquired at really a grating incidence. So maybe that their emissivity is not that important. That's why in our proposal for a compensation algorithm, at this stage we are only focusing on the KA and U band. So just to give you an idea of the radiation spread outside the wide beam region, which is the region 3 times wide the footprint one, we have these histograms of the distribution of the K percentage. I'm sorry, because the vertical axes are not at the same scale. This is expressed just to appreciate the differences changing the frequency. Because if we go from C band, where I told you that there is almost no grating lobes, we go up to Ka band, in which the contribution is important. And sorry, I was too fast. The point is also that the footprint constraints are very, very demanding, because we are going from 13 kilometer in C band up to almost 3 or 4 at Ka band. Then, as the challenges and the difficulties are many, that is great of conical scanning, no gap, whatever, we decided to separate those variables, let's say. And so at the beginning, in this phase, we only studied the grating lobes. So the acquisition configuration is not a conical one, but is a push broom-like. That is, the acquisition is done from top to bottom, left to right. This sketch map, the Picasso map, was a suggestion of the MAG of the MAG group of the SIMR, and is included in the document in MRD 3.0, and is a very challenging card because we have a sharp transition, both geometrical and as a radiometric contrast. In the table on the right, we have the level of the higher and lower brightness temperature, and that define the gradient on the shapes that are shaded. And when the shape is full, there is a constant value, which is the last column in my table. And this card is the same for all the frequencies, because when we acquire with the antenna
now.
Sorry? Okay. So I go very fast just to show you what happened when we're looking with different ends, that is a different footprint. This card is averaged and the dimension are given in number of footprints. On the right, we have the effect of the antenna, the grating lobes on the measurements. You have to pay attention to the white border, which are 1 footprint wide, a region of 1 footprint wide around the discontinuities, in which the SIM requirements want to be the error, the temperature error lower than 0.5 Kelvin. So our proposal, our compensation algorithm is described in the central part of the flow chart, and foresees a deconvolution with the antenna pattern, and then a filtering to manage the ringing effect due to Gibbs when facing sharp discontinuities. The top and the bottom part of the flowchart are the pre and post processing of the technique. The pre-processing is a upscaling, that is looking with a final resolution, the test card, the TC card, just to preserve all the antenna part and detail, which is the important thing when we want to manage the grating lobes that the antenna introduces in measurements. Then the deconvolution, we have a functional. I can say that is a unique solution. The procedure converges and the functional is convex. I don't go into the detail for sake of time, and so this is the shape of the window that we use just to manage the Gibbs ringing. I go fast to the numerical results. The numerical results for the Ka band, the Ku band tell us that if you look at the raw measurement, they are poorly compliant with the SIM requirement of having an error lower than 0.5 Kelvin. Then, if we are looking in the second column, in which the error here is evaluated over the entire map, we see that just using a regularized deconvolution, we have quite pretty good results. But if we want to be compliant at 1 footprint distance from the discontinuities, which is the more stringent requirement, we need to apply to the regular deconvolution also a filtering and low pass filtering. And in such a case, we see that a Ka band where the antenna is very, very narrow, we are compliant at 70%. On the contrary, in Ku band, because of the pattern, and we are still studying this aspect, we have better results, but we are not the 100%. Then my conclusion are that our approach is a good candidate. There are many things to go to refinement to this algorithm, but we are already working on this subject, and the main points arise a realistic scenario, which includes its actual cost line and a realistic radiometric constant. The acquisition strategy that should be, and it is at this stage, it is already a conical scanning. And the hardest part of the algorithm is the padding strategy, when we have to merge consecutive images of the observed scenario. That's all.
Okay, thank you. So we have a few minutes for questions. So switch on your microphone and ask questions, please.
I have one, just a small note.
Yeah.
On your slide number 7.
I go back.
Yes.
Yeah.
Okay. I see that the footprint is smaller at C-band than X-band. Is it possible?
Yes, because the point is how the feeder are placed, because we have 4 bands in a focal plane, and they are arranged in a strange way, because there is a problem also of accommodation, and then it could be that this is a case, because the C and the C and X band has the same feeder, which is a multi-band feeder. So they are sons of the main system, and it could be, yes.
Okay.
I'll check, but it could be, or maybe it could be my error, but I'm almost sure.
Okay. In any case, it's very, very better than the existing multi-frequency radiometers.
Yeah. This is my colleague from Torino, which are the expert of the RF system.
Okay. Okay. Thank you.
You're welcome.
Just soliciting one more question, if there is one.
Yeah. I know. Sorry.
Okay. If that's not the case, then we should switch you off.
Okay.
And, then select the next one.
Thank you so much.
Yeah, and the next one will be about comparison of 3 high-resolution real-time spectrometers for microwave ozone profiling. So now we are changing frequency, I suppose, quite a lot. And yes, it's the first author that I see here. Also, Eric.
Yes.
And I see that it's coming up. Fine.
Okay, now can you see my screen and hear me well?
Everything looks great. So you can go ahead.
Perfect. Then hello everyone. My name is Eric Sauvageat from the University of Bern in Switzerland. And yes, we will indeed change quite a lot of frequency and go for a comparison of 3 high-resolution real-time spectrometers for ozone profiling instruments. And first of all, I would like to acknowledge the co-authors that are all cited here on this front page, and begin directly with a short context on the microwave ozone profiling instruments that I will spoke about in this talk. So these are radiometers that are operated by the NAVA Research Laboratory on Mauna Loa in Hawaii. They are part of the network for the detection of atmospheric composition change, the NDAC. And so actually the number 5, MOPI5, was a new front end that was developed here in-house in Bern. And here you have some pictures where it should go after for operational operations. And so using this new front end, there was a measurement campaign that was set up last year in Bern, with the goal of studying the influence of the spectrometers that are used in ozone profiling instruments. And especially the goal was to make some parallel observation of ozone at the 110 gigahertz ozone line using 3 different digital real-time spectrometers that are listed here. So the Aquaris AC240, which is widely used in remote sensing instruments, the kind of new generation from Aquaris U5303, and narrowband, also new generation spectrometer, the ETUS USRP. And the final aim, a bit of the study, was also to see if this could explain some bias that were noticed by some users of the AC240 in their time series. And so more specifically, there was actually a preliminary analysis from this measurement campaign that was showing some first sign of biased spectra from the AC240. And so in this study, what we did was we designed a new calibration routine. And the goal of this new routine was to be able to investigate this bias a bit more thoroughly and especially see the influence of the weather conditions that could be translating a bit in the height, the brightness temperature ranges. As a secondary also was to really get the full characterization of the bias and identify obviously the sources and maybe on a more later stage try to quantify this impact of the bias on the retrieved profile. Just to present quickly a bit the two spectrometers, so the two broadband ones that I will mostly speak about. The U5303 is kind of a replacement for the outdated AC240. It has an improved dynamic range for its more ADC bits, and it uses a polyphase filter banks algorithm, which, as you probably know, results in lower side lobes compared to the classical FFT spectrometers from the AC240, and better channel separation. So for more information, I invite you to see some publications that were done last year on the subject. Now to come to the results of the campaign. So what we got was some intermittent measurements between January and June 2019 for with the three spectrometers. And here you have two example time period, April and February here on the right, with the top panel showing the kind of the average brightness temperature for the three spectrometers, and the two bottom panels that show some meteorological parameters during this period. And what you can see is that we get quite a nice range of different brightness temperature and quite a good range of weather conditions. And now focusing a bit more on the February time period, what we did was then to compare these spectrometers, and especially, and that was a bit the aim of the study, comparing the spectra using some mean brightness temperature beams. So here you have kind of the lowest temperature beams between 0 and 80 Kelvin. And so we kind of average all the spectra in this temperature brightness range together. And then on the second panel, you have the difference between the spectrometers and the reference, which is so chosen as the U5303. In green, you have the narrowband, also new generation, which agrees quite well here on this plot. And in orange, you have the AC240, which seems to be showing quite a bias. And so what we did then was to do that with the different ranges of brightness temperature, and now we will go up with the temperature. So now we have all the spectra average that shows a mean brightness temperature between 90 and 95 Kelvin. And so if we go up again, that's always for the time period of February. We can see mainly two things. That firstly, the narrowband new generation in green here agrees quite well with the broadband reference, and the AC240 seems to show consistent bias, which seems to evolve quite a lot depending on the brightness temperature that we have. And in particular, we could see that there was quite a slope changes with brightness temperature, as well as a change in the absolute bias here. And in order to fully characterize this bias, we came up with kind of three parameters trying to explain that, which were the kind of the line amplitude of the spectra, the continuum amplitude, and obviously the slope of the spectrum. And computing these parameters for the whole time series and taking the difference now only between the two broadband spectrometers, that's what we get as a result for the whole time series. And what we can see is that for the three parameters, we have quite a strong relationship with the mean brightness temperature here on the x-axis, on the absolute bias, and also if we do that as a fractional differences, we get quite a strong differences between these two spectrometers. And now come the questions: where does that come from? And that's actually very good question, still under in some investigation, but we have different beginning of answers, and one is so we get a scaling error of the line amplitude and the slopes. And the first things that come in mind is maybe nonlinearity, but that results in a broadband bias, which should be in theory kind of negligible near the hot and the cold load temperature. And actually, if we kind of model that, and what we could expect from such a bias would be kind of the black line here shown on the right. And this could actually kind of explain the bias that we see on the continuum, but that fails completely at explaining the change in the slopes or the line amplitude bias. So we also investigate the channel response of the FFT, but this is also not sufficient to explain such a bias, as well as the quantization error from the 8 bits compared to 12 bits ADC converter. This also fails, and we are left with kind of a numerical artifact in the ACE240 that would kind of lead to spectral leakage, I would say, and you will see that a bit on the next plots, but which we could kind of model using this formula here, and this would be kind of a redistribution of the mean brightness temperature, so the mean brightness temperature in the whole spectra, and that would be a bit this part with a nonlinearity effect that we could see as well. And so actually, if we now apply this kind of scaling on the reference, so on the U5003, and do the difference with the AC240, that's what we would get. So in orange is the original case, so that's a bit what you have seen already before. And now the red curve shows you applying a scaling factor of 8% on this mean brightness temperature, while the green curve shows you the same scaling factor with an addition of the nonlinearity effect that we could expect. And actually, if we now go again on different temperature ranges, so going up in temperature, what we could see is that this 8% scaling factor, and in combination with the nonlinearity effect, is able to explain quite well and correct quite well the bias that we see, with some exceptions at higher frequencies here. But this is already much better than the non-corrected case, let's say. And now to summarize quickly, yes. So we get a consistent bias from this AC240 compared to the other two spectrometers. This bias depends on the line and the continuum amplitude, therefore also on the weather conditions. And it's a combination of different sources with kind of less spectral leakage that is still under investigation, and some non-linearities. As an outlook, quickly, we aim at better constrain and quantify the bias sources, especially also quantify the effect on the retrieve ozone profiles, and especially extend also this study to other lines, for instance, ozone at 142 gigahertz or water vapor. And with that, thank you for your attention, and open for questions.
Yeah. Open your mic and ask questions, please. I see no questions on the chat.
No, nothing also from YouTube.
It seems like everybody is eager to go out, but there's a break soon, to go out and have some drinks and some talk in the hallway, and nice snacks and all that. But before that, you have to ask questions.
Okay, I have a question then. I was just wondering if you had any idea how general these results would be to, the same different models of the same spectrometer. So are they specific to the 3 that you were testing, or if other people have the same model, will they see the same results?
We kind of expect that it's general with this model of the spectrometer, the AC240, but actually some different user using different instruments, using different AC240, were seeing these kind of biases in their time series, and that's still something to prove, but it could be explained by this model having some kind of spectral leakage. And that would explain in the end the bias in the final time series. So I would expect that would kind of be general with this model of spectrometer.
Okay. Are there some other questions? If that's not the case, then it's time for a half-hour break. So we reconvene at 1700 and enjoy your drinks.
Thank you.
Okay.
You do all.
Thank you all. Please, for the presenters to the second session, do not forget to join now for verification of audio, video, and also the screen sharing in case of problem. Thank you. The other can now leave the session before for half an hour. I would like to thank the Niels and the Simone for sharing, all the presenters and all the attendee for staying connected. Thank you. Okay, we will back in a very few minutes. Okay. Shall we start with the session? We have only 3 presentations in the next session. The first one at 5 o'clock p.m. is by Aravind. Are you there? I see
Yes,
you.
I'm here.
Okay. Can you try to share your screen? Just a minute. I will give you the... Okay. You should be able now to share your screen so we can try the presentation.
Let me try.
Did you find the...
Yes, I did.
The button? Okay.
Yes.
Just
are you able to see, Manuel?
yes, it works. Try to the full screen mode.
Is it full screen?
Yes. I see some gray box, but it works. Okay, we are moving now. Good.
Okay.
Okay, good. Thank you.
Is the black box?
Yeah. I see it's some gray box. I don't know
Is it
what
gone now?
it is now. It is reduced, but it's still there. It's okay. Now is on the upper right.
Okay. I think it's
now is outside. Now is on the slide. So it's masking a part of the slide. I don't know what is.
It's the it's the window that shows other users.
Okay.
Yeah.
Okay.
So I can probably just minimize that.
Yeah, but maybe it's better during the presentation. It's possibly better. Okay.
Yeah. So I'll just minimize it and move to the.
Oh, so now we only see a gray bar on the upper right corner of the screen, but it's outside the slide, so it's good. Okay. Thank you.
Yeah. So
now
I will. So I'll stop now.
Yeah, you can release the screen.
Okay.
Okay. Igor, are you there? I see you.
Yes, I'm here.
Okay. Can you try to share screen? You have 2 presentations today.
Yes.
Right? Okay.
Yes.
Can you try to share the first one? Just a minute. I have to give you.
Okay.
Okay, now you should be able to share your screen.
Okay. Should I share my PowerPoint or screen, do you recommend?
I think that doesn't change. You can try to share the PowerPoint. Maybe it's better. But otherwise,
I have to present.
You can also share the entire screen and then go in the full screen mode with the presentation. I think it's the same.
So I have 2 presentations, so it's better to share the screen. So it's because I wouldn't have to reconnect. So this is first one, and this is the second one.
Okay, good, perfect. So it is easier. Good.
Yeah, there's no gray box here.
No. Absolutely
Interesting.
not.
Okay.
It's something funny with software. And try to go in full screen mode and go forward and back a while just to verify completely. It works. Okay, that's good.
Yeah.
Okay.
Yeah.
Good.
Okay.
Thank you.
Thank
so we
you.
can finish here the pre-session and enjoy your break. And we will be back in 20 minutes, more or less, for this session.
Thank you.
Ma che facciamo? Io faccio la PlayStation, che si è tutti messi lì qui. No, lui prova a contattare, c'è nessuno. E gli fa, se qualcuno gli asfalti gli ha occhiato di vabbè. Vabbè. Tanti sono. Dai, mi maschero anch'io. Perché certe quelli che sono in votazione di Ada perché le venuto via alla porta mia come c'è a prendere le lezioni sociali qui cioè quindi non fa e poi entrati la strada. Poi dalla donna delle pulizie di materiale, oppure giustamente va per dire o hanno fatto i tabelloni possono consigliare, sì. Poi non portino via. Sì, la Teresa fece il tabellone, no? Li tutti. Ha chiesto a tutti. No, ma deve essere anche così, perché cioè, il fatto che qui dentro nessuno, se non per dire polizia, abbia le chiavi delle stanze, se non è grave, è molto grave. Questa ossessione per la sicurezza di tutto.
Hello, I'm here. Giovanni speaking.
Ciao Giovanni, sono Ada. I tuoi colleghi si stanno facendo ridicolizzando worldwide. Non sanno che li sentiamo? Diglielo.
In italiano parlano. They
Sì,
speak in
esatto.
Italian, it seems. I am the chairman of the next session.
Ho visto, no, ma sono in pausa, però li sentono tutti.
Ok, ok.
Siamo le solite.
Come stai?
Delle mai faraoni.
Bene, però no, parliamo.
Ma Giovanni non si è visto.
Dopo.
Yeah,
Ciao.
I'm here. Emanuele, I'm here. Hello? No one hear me.
They are on coffee break. No, I don't know where.
Okay, okay. Actually, we are in lockdown in Italy, so they have to stay home. Anyhow, people already check the presentation. Yes,
Yeah,
I
yeah.
guess. Yeah, all people, all attendees are here. Yeah, good. Sorry, apologize, but I have another commitment at the same time. Really difficult to manage.
Ora ti sono il cellulare, allora inizia. C'era il tuo. Eh sì.
Giovanni, ci sei?
Yes, I'm here.
Bravo. Senti,
All the speaker try to connect. Yes.
sì, abbiamo già fatto tutta la pre-session.
Good.
E dopo o Paolo De Matteis o Ed Kim introdurranno l'RFA discussion.
Alla fine di questa?
Alla fine di questa, sì, e anche alla fine dell'altra stanza.
Ok. Che comincia però alle 6:30, giusto?
Sì. Quindi ora si guarda. Ora non ci sono ancora, per cui
Questi 3 di ora sono tutti presenti, hanno la presentazione.
presenti, sì, c'è Igor Janowski, ne ha 2 e prima c'è Aravind.
E le fa tutte
Tutte
Igor, le fa tutte e due
due.
Igor Janowski?
Sì, le ultime 2 sì.
Mhm.
Va bene. E niente, insomma, tanto questa è la sessione, poi c'è da arrivare alle 6:30, sì che
Sì.
teoricamente bisogna rispettare i 10 minuti e 5.
Sì, c'è
Però
meno fretta, c'è meno urgenza.
c'è meno urgenza, se qualcuno sfora, pazienza.
Bene.
Vabbè.
Emanuele, scusami, l'RFI c'è un programma o sono parole, è un brainstorming,
Senti,
una tavola rotonda?
è
Aspetta che mi metto il video, che così...
aspetta,
mi
è a
vedi.
metà. Se vai sul sito
Ho
e clicchi sulla cosa, c'è soltanto una
guardato,
una
c'è
breve
scritto...
descrizione. Perché
esatto,
dovrebbe essere questa
sono...
comunità che fanno almeno un paio di interventi la dovrebbero fare, ma diciamo è un evento che ci hanno chiesto di ospitare, quindi noi non lo gestiamo
Sì.
direttamente.
Ah, ok.
E quindi, però non ho, a quanto ho capito, insomma, sarà più una tavolona rotonda che non diretta,
Ok.
ci sarà
Tanto
guidata da un paio di presentazioni, ma poi se la cantano e se la suonano per conto loro fare, insomma. Per
Paolo De
intendersi.
Matteis?
Sì, e Ed Kim sono loro gli organizzatori.
Ma io un po' lo ascolterò così imparo qualcosa che non...
Può far comodo, sì.
Dovessimo finalmente fare CryoRad, Giovanni, un po' di RFI ci fan bene.
Molto bene ci fanno.
Per quello, siccome io sono abbastanza digiuna, sento un po'.
Bene.
Ma tu sei lì in istituto, Emanuele, giusto?
Sì, per scrupolo, perché avrei
Perché mi
potuto fare
sentivo
anche
fare
da
una
casa.
pausa. A un certo punto ho
Sì, si è
sentito vengo, mi
scatenato un po' di...
maschero. Ah,
Avevate i
Sì.
microfoni aperti, sì.
Sì, era rimasto un microfono aperto, sì, siamo qui per scrupolo, insomma, perché cioè, la connessione di casa, se può fare uno scherzetto, è brutto.
Ma io, guarda, poi quando abbiamo fatto la prova ho capito perché non funzionava, perché avevo acceso Skype, Teams, che noi siamo obbligati a tenerlo perché il nostro direttore è un grande fan di Teams, dobbiamo sempre essere raggiungibili. E poi avevo ancora attivo un Gmeet che avevo parlato con l'insegnante di mia figlia stamattina, quindi probabilmente tutte
Io
queste robe
domattina
qua mi
ce l'ho
hanno
già.
fatto esplodere la banda.
Guarda, meno male me l'hai detto, me lo so mettere, domattina ce l'ho anch'io un meet.
Con gli
Domattina presto.
insegnanti?
Sì,
Che
tutti a casa
tristezza.
anche. È così, c'è poco da fare.
Vabbè, però noi siamo già rossi da una settimana, se venerdì è la seconda, se siamo bravi, magari settimana prossima siamo arancioni.
No, noi ci hanno fatto il crescendo in 3 giorni. Mercoledì
Ho
scorso
visto.
eravamo arancioni e venerdì ci avevano dato l'annuncio e saremmo diventati
Ma
rossi.
perché per me arancioni è strategico, perché mia figlia è in terza media, se torniamo arancioni almeno va a scuola.
No,
Perché
i
così devo
miei...
cucinare 2 volte al giorno. Giovanni sa che io odio cucinare. Poi i ragazzini non fanno altro che mangiare, hanno sempre fame.
Ma i miei tanto mangiano solo le 3 cose semplici, odiano tutto ciò che è di elaborato e di
Però
sapore
devi
strano.
cucinarli, mica
Sì.
succhiano i surgelati tipo ghiacciolo
No,
di
tipo
soia.
ghiacciolo, no,
Eh,
quello no,
Quindi
quello
devi
no.
cucinare, devi. Invece sei a scuola, sta a scuola dalle 8 alle 5, almeno mangia là.
No, i miei ormai sono tutti e 2 al liceo, sicché non... Questa opzione non è prevista.
Ecco. Vabbè, insomma.
Vabbè, che ore sono?
10 alle 5.
10 minuti.
E poi
Chi è che sono? Allora, Igor che le fa tutte e due, mi hai detto.
sì.
Giusto.
Aravind, questo nome è difficilissimo.
Sarà un indiano, no? Aravind.
Che è connesso comunque, quindi occhio a cosa dici.
Sarà
No,
indiano.
diciamo che il nome è difficile, ma quello
Sì, è un dato di fatto.
non era un offensivo.
No, infatti.
Quindi oggi è andata praticamente.
E c'è stato 2 no show, dicevi Emanuele?
C'è stato uno show del gruppo degli svizzeri
Mhm.
e ora si ricostruisce bene cosa è successo e poi sull'altra sessione, sulla Trials Film, ha detto la Simonetta, insomma, è stato abbastanza antipatico. Perché
Sì,
già abbiamo dovuto
assolutamente.
sollecitargli parecchio per le risposte, Mike Swank aveva detto veniva lui, insomma presentava lui e poi non... Poi si è dovuto sollecitare perché non rispondeva più. Poi alla fine la risposta ha detto sì, ci sono, ho pagato, e poi via. Quindi quello è un po' antipatico, diciamo.
Che abbia il Covid? Che sai, qua in Svizzera non dicono niente, ma sono messi peggio che da noi, come contagi.
Potrebbe essere un'opzione. Non ci avevo pensato. In effetti.
Ma insomma sono diversi autori, ma almeno uno
Infatti,
no,
infatti
Tra
stavo
l'altro
trovando.
Swank non è neanche il
Poi i
primo
finlandesi
autore.
non si ammalano. Chi va in Finlandia? Scusami, dai. Sono lì.
Neanche il Covid mi sa che ci va tanto volentieri in Finlandia.
No, infatti. Cioè, a parte lui sono tutti nomi da finlandese. Juha, Juval, Tuomo.
No, ma quelli
Timo.
sono...
Questi sono svizzeri.
No, gli svizzeri è un altro paese per... Stai guardando il pepe sbagliato.
Ah, ok, il primo, sì, ok.
I
Perché
finlandesi
c'è
hanno
Mike
fatto...
Fonka.
Sì. E il primo è un altro nome, non so se è indiano anche quello, sembra, ma sarà uno studente, qualcuno. Però c'è anche Massler per dire dentro, insomma, c'è gente importante.
Manuele,
Sì?
ti avevo
Dimmi.
chiamato io sul cellulare per
Ma
dirti
quando?
5 minuti fa via WhatsApp per dirti avevi il
No,
microfono acceso.
non mi ha segnalato niente.
Ah,
Nulla.
via WhatsApp. Quindi via
Ah,
dati.
sì, ora ho visto. Sì, ho visto. Sì, infatti, vabbè, insomma, poco male.
Sì,
Mentre era
poco male.
finita la sessione. Adesso siamo alla
Certo.
tazzina. Vi piace
Va
la
bene.
tazzina?
Ciao.
Sì, sembra, non so se guardi la 7, c'è una trasmissione che si chiama Coffee Break la mattina e
No.
che ha giustamente una cosa non così bella, ma comunque l'idea della tazzina con il simbolo della pausa. Bella comunque.
No, ma è bellina comunque.
Molto, molto. Poi anche i colori, il bianco-nero, così bella.
Beh, tanto
Come si
l'ho
dice,
preso da
sobria ma
internet.
elegante.
Sobria ma elegante. Ci sta. Perché l'ho trovata su internet, spero non avere problemi di copyright, tra l'altro. No, ma era fra le immagini di PowerPoint, in effetti, eh.
Vabbè, cioè, quindi
Insomma,
l'hai già
dovrebbe
pagata.
essere... Sì, sì. Va bene. Boh, niente.
Il technical manager qui che lo fai te, no? Chi è?
Lo faccio io, sì.
Ah, ok.
Faccio tutto, faccio.
No,
Perché
se vuoi lo facevo io, era per alleggerirti, dicevo.
No, va bene, tanto sono tre a passare. Io praticamente passo la palla e guardo le domande su YouTube e semmai te le riporto in chat se ce n'è qualcuno
Sì.
che chiede per tempo, perché ieri è successo più di una volta e abbiamo scritto dopo.
Con
Cioè,
il delay
già
del tempo.
sì, vabbè, c'è 10
Vabbè.
secondi di ritardo, ma questa domanda è arrivata tipo un minuto dopo che si era già a un pezzetto avanti sulla presentazione successiva, quindi...
Vabbè, pazienza.
Ma il YouTube che è il session manager che sorveglia YouTube?
Sì, si è fatto così, cioè che io, insomma, il session manager gli dà un'occhiata ogni tanto se c'è... Lo streaming va da sé e se appare
E lo
qualche
ributta
domanda
su
in chat, la copia e la ributta sulla chat di WebEx.
Comunque, insomma, anche oggi in questa sessione c'era una attendance di una settantina di persone fra WebEx e YouTube. L'altra
No,
non
ma
lo so.
è una formula che funziona, secondo me, così.
Sembra, sì. Secondo me lo YouTube andrebbe comunque considerato perché, vabbè che non dà profitto, però ti allarga la visibilità del meeting e non costa neanche tanto metterlo in piedi, insomma, non è che è una cosa costosa.
Quando hai garantito la parte finanziaria lo puoi aprire, insomma.
Sì,
Una volta
sì.
che hai garantito la partecipazione da un punto di vista finanziario, puoi aprire per
Sì,
disseminare
e ti
più
dai più visibilità.
visibilità, certo,
Sì.
assolutamente.
Certo è che 10 minuti sono pochissimi, numero uno, però mi rendo conto che vabbè, non si può fare dalle 8 alle 5, se no c'è certa gente che non può dormire per
No,
seguire la
infatti,
mattina.
No, purtroppo
infatti
no.
c'è quel limite
Certo,
è
ma quello
questo,
per
sì.
forza fuso orario è...
Infatti. E
Infatti mi ha
insomma
fatto
stava...
morire il tuo amico giapponese che lo chiama Bucci-san, che ha iniziato
Sì.
good afternoon, good morning, good afternoon, good evening, ha salutato
Sì, ma
tutti.
anch'io comincio, io quando faccio l'introduzione più o meno dico la stessa cosa, perché siamo più o meno, cioè la maggior parte è Europa e Stati Uniti ovviamente, però
Sì.
insomma c'è anche russi, c'è giapponesi, c'è qualche cinese, quindi loro poi sono messi male.
Ah certo, loro cosa hanno? 8 ore?
Dipende perché anche lì
Sì,
credo ci
alla
abbiano almeno
fine è
un paio di fusi,
enorme.
ci abbiano almeno un paio di fusi orari, comunque 7-8 ore di differenza, sì. Quindi le 7 di sera da noi siamo a notte fonda.
Sì.
Magari ora interrompiamo di parlare italiano perché stiamo
Vabbè,
vicini
ragazzi, dai, io
alla
anche
mezza
tolgo
della
anche
sessione.
l'audio.
Se
Ok,
no, insomma, siamo
sì,
un po'
sì, ora
troppo
va bene.
Good
razionali
job.
Alla fine
popolari.
iniziamo. Va bene. Vai te Giovanni, non ti faccio un'introduzione, tanto
No, voglio io.
vai,
Tanto,
ok.
tanto cominciamo alle 5 sharp.
Sì, cominci alle 5 e io ti do solo assistenza per passare ai presentatori e eventualmente domande su YouTube.
Ok,
Vai. Che ore sono adesso? Fra un minuto o due
56.
levo la tazzina fra poco.
If someone is connected, you can learn a little bit Italian since you did the travel, but you can learn something. I hope.
Is Babel included in the package?
Yeah.
Sure. Next edition, we also provide the Google Translator.
Yeah. So we can wait few minutes. It's 3 to 5. So we start at 5. Aravinda, are you there?
Yes, I'm here.
Okay, very good. Because you are first. Aravind, where are you based?
I'm a graduate student at CU Boulder, Colorado.
Okay. So it's morning for you, yeah?
It's bright and early.
Early morning, yeah.
Not too early. It's 9 o'clock already. So.
No. When the meeting starts.
When the meeting starts, yes, it's 6 in the morning.
It's really early in the morning.
But that's good.
Yeah.
Good to get up.
Yeah. great. So just one minute left, and then we start.
Okay. In the meantime, I can leave the ball to the first presenter.
Yes. Yeah. Okay. So yeah.
So now, Arvind, you should be able to share your screen.
Yeah. Yeah. If you can try, so we are already in the. Okay. That's good. Sound good. If you put in presentation mode, it's a little bit better for the audit. Okay, good. Great. So it's 5 o'clock sharp, so we can start. Good morning or evening. There are not many people now, so it's a very small section, and then there are just 3 presentations this evening, but I'm sure that will be very interesting. So the first presentation is titled High Spectral Resolution V-band Digital Correlating Spectrometer for Weather and Climate Application. And the speaker is Dr. Aravind Venikantsubanoni. Sorry for pronouncing, it's really difficult for me.
Oh, that's okay. Good morning and good evening, everyone. I'm Aravind Venkatesubramani. I'm not yet a doctor. I'm a graduate student at CU Boulder at Colorado, United States. I'm working with Professor Albin Grzewski, and today I'll be talking about my work, which is high spectral resolution V-band digital correlating spectrometer for weather and climate applications. Separating, quantifying, and predicting changes in atmospheric temperature, which are of climatological origin, has been identified by many studies suppressing need. The weather satellites such as MSU, AMSU, and ATMS, they were designed with weather applications in mind and not really with the precision and stability required for separating climate trends. And so we need instruments with stability and absolute accuracy much better than these to separate climate trends. Also, the variations in the parts of the 50 to 58 gigahertz spectrum observed by different sensors vary across missions, and the subchannel variations across missions is also a source of inter-satellite sensor calibration errors. Also, as we all know, with the increased anthropogenic radio emission expected at V-band due to 5G, we'll need RFI detection and mitigation as an indispensable feature for future accurate temperature retrievals. With these in mind, we are motivating the need for a high spectral resolution digital correlating spectrometer at V-band with stable down conversion to precisely characterize the variations within a wide 8 gigahertz sounding band, and also perform real-time RFI detection and mitigation. We are presenting the design, simulation, and build of such an instrument, what we name as V-band ultra-stable climate monitoring radiometer, or View Climber, being developed at CU Boulder at the Center of Interest for Environmental Technology. It is discussed. So we have put together a prototype View Climber instrument using waveguide components, WR19 waveguide components. So the Magic T at the front combines the signals from the horn and the noise diode to generate the sum and difference path signals, which are then coherently down converted with the gun oscillator at 50.1 gigahertz. The RF LNA gain and the bandpass filter response are steeply rolling off below 50.1 gigahertz, and therefore there's no problem from the mixer's lower sideband image. This RF front end draws close to 3.5 watts, and the majority of the power draw is from the gun oscillator. We are also designing an 8 gigahertz IF subbanding down converter, a single board to ideally amplify, filter, and separate the 8 gigahertz wide IF subband into 4 different 2 gigahertz subbands. This is all designed using commercial off-the-shelf components. Adequate amplification, filtering, and padding are added at each different stages to ensure that we are not exceeding the power level or saturating any of the amplifiers. This IF board design is currently under the way. We are also planning to use the Xilinx RF SOC device for digital detection. The RF SOC has 8 ADCs, each capable of 4 gigasample per second, providing 16 gigahertz of instantaneous bandwidth in one unit, thereby combining ADCs with FPGA processing fabric, creating real-time processing of the data, very much possible for such a wide bandwidth. As I mentioned earlier, the 8 gigahertz of IF that we'll be obtaining after down conversion with the 50.1 gigahertz local oscillator is subdivided into 4 different subbands A, B, C, and D. And this will be this is ensured in such a way that the different ATMS bands falls in one of the 4 subbands. And each of the 8 ADCs provide 2 gigahertz of instantaneous bandwidth. So in the correlating mode of operation, we will be able to get all the 4 subbands completely covered with one RF SOC device. So the good thing with going with commercial off-the-shelf components was that we found that most of the components that we were planning to use, the filters, amplifiers, isolators, splitters, they all are well characterized by the manufacturers, and they are available as touchstone files for use. We ran a comprehensive AWR simulation for the entire IF board, including all the amplifiers, filters, and mixers. And we're able to notice that the existing ATMS bands fall well within the 4 different subbands that we were able to achieve after going through the entire IF chain. We also noticed that there is some amount of aliasing occurring at subband edges due to folding. It is the COTS filters we have selected the COTS filters in such a way that the aliasing falls down to less than 30 dB immediately, so that there is minimal folding effect, but any residual effects of aliasing due to the spectral folding will be properly compensated and calibrated out. While we are designing the single IF down converter board to down convert all the 8 gigahertz spectrum into 4 subbands in a single board, we were able to procure connectorized COTS components to look at different parts of the 50 to 58 gigahertz spectrum one by one. This was done mainly to understand the RF front-end performance without waiting for the completion of the IF subband down converter development process. The 8 gigahertz wide IF was completely spanned with the different available filter pairs that we have at the lab, and the data acquisition was able to be carried out one subband at a time using a TI high-speed data capture board and a dual-channel ADC evaluation board, which is capable of giving up to 3 gigasample per second and a dual channel 14-bit ADCs. We were able to characterize the front end from 50.1 to 53.6 gigahertz in this mode of operation using different filter pairs, looking at different parts of the 8 gigahertz wide IF chunk by chunk. In the total power mode for path 1 and path 2, we observed that there is about 2 Kelvin of delta T RMS for an FFT resolution bandwidth of 4.8 megahertz with an integration time of 17 millisecond. And in the correlating mode of operation, which we were able to obtain using the cross power density measurements, the delta T RMS was close to 3.5 Kelvin. The delta T RMS of an ideal correlating radiometer is square root of 2 times that of a single-ended one. We observed that the delta T RMS that we observe is slightly greater than what we would expect compared to the ideal scaling factor of root 2. We need to investigate why the difference is being caused, whether it could be due to common mode noise, which is appearing as correlated noise in both the receiver paths. And so we are currently completed the RF front-end characterization for the correlating front-end from 50 to 53. We have to complete the 54 to 58 gigahertz spectrum also. We have the necessary filter pairs for that. The layout, fabrication, and testing of the single IFPCB also will be completed. The real-time data processing and the firmware development in RFSOC is also under the way. And finally, to mature the instrument concept from a laboratory prototype to a low C-swap sensor, we are planning to replace the waveguide-based front end to a single SIGI mimic chip, and we're working with Professor John Kressler and group at Georgia Institute of Technology, and also to port the firmware that we developed in the RFSOC to an ASIC-based processor. We'll be working with the Pacific Microchip Corporation. So in conclusion, I've motivated the scientific need of uClimber, an instrument for covering the entire 50 to 58 gigahertz oxygen band for precise temperature sounding. We are able to test and evaluate the initial prototype benchtop uClimber sensor, and also the IF subband down converter and digital backend hardware. We are able to successfully demonstrate proper working in the 50 to 53.6 gigahertz spectrum of the prototype instrument, and the instrument performance looks promising. Quickly to acknowledge NASA for the support they extended to the project through the NESSF award for me, and also Xilinx and Texas Instruments for their hardware and software donation programs, and also our lab manager, Mr. David Kraft, for the waveguide mounting help that he has extended. Thank you.
Thank you, Aravind, for the nice presentation. I don't see any question in the chat. Probably for YouTube, we have to wait a little bit, if any. I don't know if someone in the audit have question for you. Otherwise, probably I have one because I'm missing, which is the resolution of in terms of spectral resolution.
So the spectral resolution that we are using the data in offline processing mode. So the plots that I've generated are for a 4.8 megahertz of FFT bin resolution and an integration time of 17 milliseconds.
Okay. Mm-hmm. Yeah. So okay, that's true. Okay. For the calibration, because you have to go quickly, so I've not looked into detail the receiver. Yeah. How did you calibrate the receiver?
So it's because of the amount of data volume that we have. So essentially, because of the fact that we still don't have the real-time processing done, we have to. There's a delay between how much time elapses between the horn observes the absorber at room temperature and liquid nitrogen. So it is of the order of a few minutes. It's not ideal. So that's the reason why we are trying to increase the trying to fast forward the development of real-time data processing.
Mm-hmm. Okay, thanks. I don't see any question in the chat or either in the room. So this wideband, it's a very high level topic now. So I guess it's interesting for all application and also for other frequencies. So I guess that it's will be a subject or also additional study in future. Okay, so thanks again, Aravind, and then we can probably move to the next speaker, which is
Giovanni, I do confirm there are no questions on the YouTube chat, so we can move.
Okay, we are right in time. Thanks for your time, either. And then we can move to the next speaker. We have two presentations by the same presenter, which is Igor Yanovsky. So okay, you can maintain the ball for all the times, I guess. And we have two presentations. The first presentation is titled Spatiotemporal Resolution Enhancement for Geostationary Microwave Data. So please start, Igor.
Igor, you are muted.
You are muted, Igor.
Thank you. Thank you, Giovanni. Thank you, Emmanuel. Sorry about this. My name is Igor Yanovsky, and my collaborators are Jin Chin and Bjorn Lambertsen. I will be talking about an approach for enhancing the spatial temporal resolution of remote sensing sequence of observations. So before describing the convolution, let's first describe the convolution and additive noise model. On this slide, let U be the physical scene, K be the convolution kernel, or point spread function, or PSF for short, and N be the noise function. The equation here describes the convolution and additive noise model, where we arrive at observation F, which is a blurred and noisy image. So convolution is a well-posed problem shown in this diagram as a forward model. Here we see the equation from the previous slide. So this equation maps U, the physical scene, into observations F. The convolution, on the other hand, is highly ill-posed inverse problem, consisting of two terms. The first term here is the regularization term. In this case, it's total variation regularization, which imposes smoothness on the reconstruction. And we will look at total variation term later in this presentation. The second term is the similarity, or also called a fitting term or fidelity term, which imposes constraint on the residual of the convolution problem here. This slide shows a result of solving this deconvolution inverse problem. We have a blurry and noisy image on the left, and we recover a construction on the right. To gain some intuition about total variation constraint, let's consider a case where we have a 1D signal rather than a 2D image. So total variation TV measures variations of U without penalizing discontinuities. In one dimension, if U is monotonic in this interval between 0 and 1, then TV of U is the difference between the values of U on its edges, regardless of regularity of U. TV does not have a preference for either one of these two functions in one dimension. The total variation for these two functions are being identical, which means that total variation will not penalize edges that look like this, which we want. We don't want those edges to be penalized or smoothed out. On the other hand, a well-known linear Tikhonov regularization would prefer the smooth solution, and we want to avoid that. TV regularizes the jumps of geometry and boundaries, and TV can be extended to vector-valued functions, for example, multispectral and hyperspectral images. And in images, the minimization of the TV norm does not penalize edges in an image, in 2D images or 3D images. The proposed deconvolution method employs total variation regularization and solves the problem using the split-Bregman optimization algorithm. The split-Bregman optimization framework can be derived from the well-known alternating direction method of multipliers, or ADMM. This methodology is based on current research in sparse coding and compressed sensing, and it leads to unprecedented efficiencies for solving image reconstruction problems. So the methodology is the state of the art, it's current research. It minimizes noise amplifications, preserves edges, and does not produce artifacts. It uses a robust mathematical framework. It is based on functional analysis and variational formulations, and it can be performed in real time using very fast solvers. So here we use, here I will introduce some background on the instrument that we're considering doing experiments for. So it's observations of atmospheric wind, storm processes, and boundary layer processes are essential for assessing weather and climate. Critical regions within dynamic weather systems are commonly either obscured by clouds and rain, where microwave sounders have a large advantage over other sensors, or they're rapidly evolving, where geostationary sensors have a large advantage over low orbiting satellites. The geostationary synthetic aperture radiometer, or GeoStar for short, is a geostationary microwave spectrometer aperture system, synthesis sounder, that has been developed at the Jet Propulsion Laboratory that can provide such observations. It measures 3D field of temperature, water vapor, clouds, precipitation, and wind in large area below the host satellite. So a microwave sensor has a limited spatial and temporal resolution. In particular, a microwave aperture synthesis system is characterized by spatial blurring and distortion, which produces reading artifacts and sharp edges and other transitions in the observed field. Temporal resolution of the sensor is limited by the frame rate and by the exposure time. GeoStar produces spatial temporal oversampling that lends itself to digital resolution enhancement techniques. With such a methodology, the value of the GeoStar observations would be greatly enhanced. And we perform resolution enhancement in the space-time domain, as opposed to solving the deconvolution problem for each observation. And simultaneous space-time optimization achieves a more efficient and more accurate reconstruction. So a blurred sequence of observations is assumed to be generated by convolution of a physical scene with a spatio-temporal convolution kernel, whose two-dimensional spatial component is the microwave instrument's point spread function, and whose one-dimensional temporal component is the rectangular kernel with sensor exposure time as its support. GeoStar spatial PSF is a two-dimensional sync-like function showing positive and negative excursions, which blurs the resulting images and creates artifacts. Also, temporal blurring occurs when the scene evolves faster than the sensor refresh cycle, such as with intense convective precipitation. And here we tested the spatial temporal resolution enhancement method on simulated microwave 150 gigahertz channel image sequence of the 2005 Atlantic Hurricane Rita. Each image consists of 36 frames at 10-minute intervals, and this figure shows one of the frames. Each frame is 402 by 402 pixels, and we use the spatial temporal convolution kernel, whose two-dimensional spatial component is the geostar kernel, and whose one-dimensional temporal component is the temporal rectangular function to blur the image sequences. And here we show that our method reduces the errors in the corrupted sequence. So the error before reconstruction is shown here, and the other after reconstruction is shown here. And this is the reconstructed frame that we were able to recover with our method, spatial temporal resolution method. Thank you. Are there any questions?
Thank you, Igor. Thank you also to keep in time. 10 minutes are not so long, but you did a good job. There are any question in the chat or from people that is in the room that they can open also the microphone if they prefer? No question. I have a question for you if anyone have it. How the method works on the edge, because in general the problem of this technique is how to reconstruct the image on the border of the acquisition, from where the information come from. How did you have some comments on it?
So the model is designed for capturing edges. So if there's big transitions in observations, these edges are going to be preserved. So we don't smooth over edges using our model. Like most models that are there, they smooth over edges. But when we have a strong convective systems, we need to preserve those edges. Such hurricanes. Hurricanes also have edges and observations. So that this method is designed to preserve such edges. And it does it pretty well.
Okay, and when you are at the limit of the SWOT, how it works?
It works just as fine as for the interior of the swath, except for, of course, there may be some distractions due to FFT, but we didn't experience such problems. So there are considerations about this, but they don't affect us that much.
So did you discard the pixel that are close to the far part of the SWOT or not?
No, the pixels, as we see here, we used all pixels in the image. So if we look closer here, the parts here are affected by FFT in our simulation, but we are able to recover a nice representation of the reconstructed image closer to the boundary.
Can I ask one question?
Yes.
Yes.
I'm Hyuk Park. Actually, you told me that it could be implemented as a real time. So could you tell me the processing time of the one image?
It depends to which accuracy we want to solve our algorithm. So for one such image, to run the entire algorithm, just to be sure we converge to the highest possible precision, it takes about 15 seconds or 14 seconds. But it's enough to get, if you want to get an accuracy which is 98% of that,
the algorithm would reconstruct an image maybe in one or a fraction or a second, one, two, or even a fraction of a second per image.
Okay.
And
okay, if I can add one more things, sometimes this kind of the convolution is impacted by very high one peak like RFI. So have you tested the RFI case, which is quite strong and contaminated less contaminate the image?
So there are different considerations. The noise. So when you say 1 pixel contaminated, you're probably talking about speckle noise, right?
No, my meaning is that the one high strong RFI source could be as a one very strong point source, and the synthetic aperture radiometer case, the point spread function is the quite high side lobe and the shape of the Y. So have you tested that kind of case? If our image is measured with the one strong RFI together?
No, we haven't tested that. Yeah, I have to see in order to see how it would perform, in order to get a feel like I really have to see the data.
Yeah. Of course, we have to mitigate the RFI source contamination first, but sometimes we have to check that in the case the RFI source is the captured case or not. Okay, thank you.
Okay, thank you.
Okay, we have to move to the last presentation of this small session, which is already by Igor, in my understanding. So you can move from the next presentation, which I don't know if it is also on the same topic, because it's an effective super resolution reconstruction method for geometrical deformed image sequences. Is Igor? The ball is yours.
Yes, thank you. Thank you, Giovanni. So this is the second talk, and for those who didn't attend the first talk, my name is Igor Yanovsky. My collaborator is Jin Chin, who is the first author on this project, and I will be talking about an approach for super resolution reconstruction for geometrically deformed image sequences. So this is a very different application from what I presented in the previous talk, and therefore the model is also very different, even if we'll be using much of the same data in this talk. In the previous talk, we considered geostationary spatial temporal data taken over a period of time. In this talk, however, we consider an instrument capturing multiple images at nearly the same time while undergoing some motion. Here, we also assume that the images are of very low resolution, so we need to account for upsampling in our algorithm. So we first describe the forward model of convolution and downsampling in this time. On this slide, let U be the physical scene, K be the convolution kernel or PSF, D be the downsampling operator, and epsilon be the noise function. The equation here describes the convolution downsampling and additive noise model, where we arrive at observation F, which is blurred, downsampled, and noisy image. So this slide shows different types of super resolution problems. Figure on the left here shows a problem of super resolution of multi-frame image sequences crafted with noise and noisy point spread functions. The image to the right shows spatial and temporal resolution enhancement from continuous and sampled observations. So these are also different super resolution applications that also require different models. So there are different kinds of super resolution problems, and they're all different. This slide just tries to stress that. There are challenges for achieving super resolution. There's a presence of noise, such as shot and quantization noise due to atmospheric effects. There is blur, such as Gaussian blur due to the light sources and movement of sensors elements.
There are sampling artifacts such as errors due to the upsampling operator. And there are also geometrical deformations, such as translation and rotation by a certain angle. And to simplify the discussion, we consider the processing the set of low-resolution images using some registration toolbox. We assume Gaussian noise. We assume that we are dealing with a Gaussian blur, and we assume the sampling errors by designing a variational method. There are a variety of super-resolution reconstruction methods, including learning-based methods, which create a redundant dictionary and find a sparse representation. There are interpolation methods, such as polynomial interpolation. There are frequency domain-based methods, which perform reconstruction in the frequency domain. There are probability theory-based methods that use Bayesian inference, for example, maximum a priori method. And what we are considering here are actually variational methods, which build a variational model and solve it by some optimization algorithm. This is something we are considering here. We consider total variation TV for regularization. TV measures variation of a function without penalizing discontinuities. It preserves edges in an image. It regularizes the sizes of jumps and geometry of boundaries, and TV can be extended to vector-valued functions. We further extend TV to non-local total variation, or non-local TV. The non-local TV fully exploits non-local similarity of images, and it has been applied in image processing. So we now describe the proposed mathematical model. Given Bk, a sequence of low-resolution images, X, the high-resolution image to be reconstructed, Fk, the geometric motion operator between the high-resolution image and its corresponding low-resolution images, Hk, the blur operator and sensor blur, and Dk, a downsampling operator. So we propose the following super-resolution reconstruction model, where the first term is the L1 term, L1 norm, data fidelity, and the second term is the non-local TV regularization. For data, we consider the 402 by 402 simulated microwave 150 GHz channel image of the 2005 Atlantic Hurricane Rita with a resolution of a pixel of 1.3 kilometers. So here we're looking at not at spatial temporal data, but just at 2D data, spatial data. For simulation, we set up the simulation as follows. We generate a sequence of 64 low-resolution images of size 100 by 100 with intensity range between 0 and 255 by applying the following operators to the ground truth subsequently. We perform geometric deformation, including clockwise and counterclockwise rotation by 1 degree and translation diagonally and anti-diagonally by 1 pixel. We remove dark boundaries due to the geometric deformations in MATLAB. We use 3 by 3 convolution Gaussian kernel with standard deviation equal to 1. And we downsample with sampling factor of 4. So we take the observation and basically rotate it and translate it and downsample it in order to get to the simulation data set. So right now we want to reconstruct the high-resolution image from this data set of rotated and translated and downsampled images. So Here, we compare our algorithm to the state-of-the-art bilateral total variation, or BTV algorithm. First, we tested the proposed algorithm and BTV on the noise-free data. This figure shows the reconstructed high-resolution images with close-up comparisons of small regions outlined by yellow lines. From the results, we can see that BTV result has slight staircase artifacts, while the proposed one can preserve details more accurately. The proposed algorithm is good at preserving local geometries by utilizing the non-local image patch similarities. The peak signal-to-noise ratio is also higher for the proposed algorithm. In this experiment, we test the robustness of the proposed algorithm to the Gaussian noise case. Whereas Gaussian noise with zero mean and standard deviation equal to 1, 2, 3, and 4 and 5 is that on the previous set of low resolution images. We know that noise can cause an inaccurate estimation of the displacement fields during the registration step. This table compares the performance of the bilateral TV and the proposed algorithm using the PSNL values of the reconstructed images under various noise levels. We see that the proposed method outperforms the bilateral total variation method. For conclusions, multi-frame super-resolution sensing, remote sensing image reconstruction problem is highly ill-posed inverse problem due to the complexity of multiple degradation operators, including blur, sampling, and geometric deformation. We proposed an effective super-resolution image reconstruction method based on non-local TV regularization and L1 norm data fidelity. This promotes the robustness and the performance enhancement. The proposed algorithm is able to produce high-resolution images with higher accuracy and visual quality than the bilateral TV-based method. The proposed approach is robust to various noise types. We will develop and extend the proposed work by further taking advantage of the tensor structure to reduce the computational cost and simplify the formulations in the near future. Thank you. Are there any questions?
Thank you, Igor. I don't see question from the chat now. I don't know in YouTube channel if any or anyone.
Can I ask one thing more? No?
Oh yes,
Hello?
yes, sure.
Yeah. I'm okay. Yeah.
Go ahead.
Actually, you use the 64 sequence of the snapshots for your. Hello?
Yes.
Okay.
Yes. I hear.
So have you tested the image quality improvement with respect to the number of the sequence?
No, but not in this work. In a different work, we use a different algorithm where we test it, and as we expect for this work, the larger the sequence of images is, of course, we would get a better
get better, but there will be some stagnation point that increment will not be, the high
observable.
Anymore,
Yes, yeah, we can expect that. Yes.
Yeah, so that kind of things will be interested in the. Of course, the main assumption is that the image should not be quite much different in a whole sequence. But,
yes.
That will be somehow interesting, I think.
Yeah. Thank you for your question.
Okay. Any other question or comment for Igor from the room or from YouTube or whatever?
No, Giovanni, I do confirm that there are no questions posted on the YouTube chat.
Okay.
At the moment.
Okay, so I guess that if no other question, we can close here this session. Thanks. It was short, but it's really interesting because also this methodology can be applied to other sensor, other instrument, and so on. It could be a general interest for anyone. And the session closed here, but before closing, I believe that we have to leave the ball to Paolo De Matteis that present us the special event that we have the afternoon or end of morning for US colleagues on RFI meeting that start at 6:30, and you have a special links which is on the web page of the conference. Paolo, did you want to say something?
Yes, but
Paolo, do you need I share the slide we were discussing before? This one?
Yes. Okay. Yeah. Thanks for unmuting me. I couldn't unmute myself. So hello everyone. Yes, if you can share it, or I can share it.
Yes, it's now ready.
Just go ahead.
Do you see the slide? It should be on.
Yes.
Okay.
Well, it's still about up here. Okay. So I would like to announce, Emanuele already and Marco already mentioned, we organized a meeting to discuss some issues related to radio frequency interference. And this meeting is going to start 6:30 Central European Time. We cover two topics: NSF Center that is being planned, and also the NSF Center for Spectrum and Innovation. And then we have a discussion on proposal by the Helga Committee to develop standards for RFI impact assessment. So this is going to be very interesting and topics, in my opinion. So I encourage everybody to join, and even if you're not too much into radio frequency interference, I think these are important issues that should be known to the passive community. Okay, hope to see you there. You have to use the link that is posted on the MicroRad main page. And that's it. I hope to see you there.
Okay. So I believe it concludes this session, and thank you to Giovanni for chairing it. Thank you to all the presenters, and thank you to all the attendants for this well-followed session. Just
Thanks,
for
Emanuele.
information, we are about 30 attendees on WebEx and almost the same number on YouTube. So considering we have the split in two sessions, I believe is a good result for today. Thank you.
Thanks, Emanuele. Bye. Ciao.
Ciao.